What lies beyond the boundaries of all that we know? For thousands of years, this question has tugged at the edges of human curiosity, prompting our species to peer deeper into the unknown, to stretch the limits of imagination, and to seek understanding through science. We have journeyed from the earliest myths of the cosmos to mind-bending theories that challenge even the most steadfast notions of reality. Concepts like a cyclic universe, where existence endlessly ebbs and flows in cosmic repetition, or the possibility of extra dimensions woven into the fabric of space-time, as predicted by string theory, have shifted our perception of what is possible. We stand on a precipice where revolutionary ideas intersect. Dark energy dictates the expansion of the cosmos. The holographic principle questions whether space itself is an illusion, and quantum fluctuations hint at the creation of entirely new universes. Each revelation forces us to confront profound questions about our own existence. Are we mere inhabitants of a vast multiverse, one bubble among countless others? Or could everything we perceive be a sophisticated simulation, a cosmic illusion engineered beyond our comprehension? The observable universe, the portion of reality we can perceive from Earth, encompasses all matter and energy detectable by our instruments, stretching outward in every direction until it meets the limits of what light has managed to reach us since the universe began roughly 13.8 billion years ago. Yet this boundary is not a wall in space, nor a cosmic edge. It is the threshold imposed by the finite speed of light. Even light, the fastest phenomenon in the universe, is not instantaneous. The beams that stream from the farthest galaxies take billions of years to traverse the void, a journey that spans cosmic epochs. The most distant light we detect today began its voyage almost at the universe's birth, when the cosmos was only a few 100,000 years old, a mere infant by cosmic standards. Thus, when we peer into the farthest depths of space, we are not only gazing across unimaginable distances, but also peering backward in time, glimpsing the universe as it once was, a silent observer of the past. Closer to our cosmic neighborhood, the celestial objects appear as they were more recently, and our understanding expands continually as light from ever more distant regions reaches us. However, due to the ongoing expansion of space itself, some portions of the universe remain forever inaccessible. These areas lie beyond our cosmic horizon, eternally beyond detection, creating a tantalizing juxtaposition. The observable universe is vast, yet it is merely a finite window onto a potentially infinite cosmos. The diameter of this observable sphere measures an extraordinary 93 billion light-years, encapsulating countless galaxies, each containing billions of stars and an uncountable number of planets. Even as we explore, we are reminded of our smallness, a single consciousness embedded within the immensity of space-time. This cosmic horizon is dynamic. It continues to expand as time passes and light from previously unreachable finally arrives. Yet the expansion of the universe complicates our view. Space itself stretches, elongating the light waves emitted by distant galaxies, shifting them toward longer, redder wavelengths in a phenomenon known as redshift. For objects at extreme distances, this redshift renders their light invisible to conventional optical instruments. Additionally, the early universe was opaque for nearly 400,000 years, filled with a dense fog of hydrogen plasma. Only after this period, known as recombination, did the cosmos become transparent, allowing photons to travel freely and light to illuminate the darkness. Events occurring before this era are obscured, unreachable to direct observation through electromagnetic radiation, marking another boundary in our quest to understand the cosmos. Our cosmic horizon, therefore, is not a physical limit, but a frontier defined by the interplay of light, time, and expansion. As we look further into space, we look further into the past. Light from the edge of our observable universe has traveled for roughly 13.8 billion years. Yet because space itself has expanded, the current distance to those regions is much greater than the distance light has traveled. This expansion ensures that the observable universe encompasses a radius of approximately 46 billion light-years, a number far larger than a simple calculation based solely on the age of the universe would suggest. Beyond this lies the unobservable universe, regions whose light has not yet reached us and may never do so. Over time, as light from ever more distant regions travels toward Earth, the cosmic horizon stretches outward, slowly revealing previously hidden expanses. Our understanding of the universe's scale has undergone a dramatic evolution. Early civilizations envisioned a cosmos centered around Earth, fixed stars decorating a celestial sphere, and the heavens as a static, unchanging stage. The scientific revolution shifted this perspective. In the 16th century, Nicolaus Copernicus proposed a heliocentric model, placing the sun at the center of our solar system, fundamentally altering humanity's place in the cosmic story. Yet, even this revelation was dwarfed by the early 20th century work of Edwin Hubble, whose observations revealed that our Milky Way was just one galaxy among hundreds of billions, each stretching across the void, collectively creating a universe whose scale defies comprehension. Today, modern astronomy and space exploration have revealed an observable universe 93 billion light-years across, with countless galaxies, stars, and planetary systems, an infinite complexity that continues to expand as our instruments improve. To peer into this vast expanse, astronomers deploy a remarkable array of tools. Optical telescopes, both terrestrial and spaceborne, capture visible light from distant stars and galaxies, including massive instruments like the 30-meter class telescopes and the Hubble Space Telescope, whose discoveries have reshaped our understanding of the cosmos. Beyond visible light, the electromagnetic spectrum opens new vistas. Radio arrays, such as the Very Large Array in New Mexico, detect radio emissions from celestial phenomena. X-ray and gamma-ray observatories, including Chandra and the Fermi Gamma-ray Space Telescope, reveal high-energy processes from black holes to supernovae. Infrared instruments like the James Webb Space Telescope peer through cosmic dust to uncover stellar nurseries and distant galaxies. Ultraviolet telescopes expose young hot stars and active galactic nuclei. Each wavelength illuminates a different facet of the cosmos, providing a holistic picture of the universe's complexity. Emerging technologies augment these classical tools. Adaptive optics correct for atmospheric distortion, interferometry synthesizes multiple telescopes into virtual giants, and supercomputer simulations model cosmic processes across billions of years. Gravitational wave observatories such as LIGO add another sense, allowing humanity to hear cosmic collisions and explore the fabric of space-time itself. Through these lenses, we witness a universe in motion, galaxies receding, light stretching, matter coalescing, and space itself expanding. The phenomena of redshift, cosmic opacity, and horizon limits are not mere curiosities. They are the tools by which we chart the universe, revealing a cosmos both vast and intricate, endlessly challenging our understanding, yet inviting us to continue the exploration. This is a cosmos that defies intuition. The universe is not static or bounded in the ways our minds find comfortable. It is dynamic, ever-expanding, and partially hidden, a dance of light and time across unimaginable distances. Each discovery, each new photon captured extends the horizon just a bit further, revealing the grandeur and complexity of existence on a scale that humbles, inspires, and endlessly intrigues the human spirit. However, the expansion of the universe is far more than a mere stretching of space. It serves as an indispensable tool for astronomers and cosmologists to probe the vast cosmic expanse. By meticulously analyzing the red shift, the lengthening of light waves emitted by distant celestial objects, scientists can determine not only the distance of these objects from Earth, but also the velocity at which they are receding. This dual measurement allows for the construction of detailed maps charting the large-scale structure of the universe and tracing its evolutionary history from the first fractions of a second after the Big Bang to the present epoch. The universe's expansion inherently defines a limit to what we can observe, a boundary known as the observable universe. Beyond this cosmic horizon lies a region where light has not had sufficient time to reach us since the universe's inception. As space continues to expand, galaxies once visible in the night sky will eventually drift beyond this horizon, disappearing from view and becoming forever inaccessible to our instruments. This realization emphasizes the dynamic and transient nature of our observational window into the cosmos. Embedded in the fabric of space itself is the cosmic microwave background, a faint, omnipresent glow of radiation that serves as a relic of the early universe. Originating roughly 380,000 years after the Big Bang, This radiation represents the earliest light that was able to travel freely once atoms formed and the universe became transparent. Observing the cosmic microwave background is akin to peering at the edge of the observable universe. It marks a horizon beyond which direct observation is impossible. Its uniformity across the sky provides compelling evidence for cosmic inflation, a brief yet extraordinarily rapid expansion in the universe's infancy, which helped render the cosmos remarkably flat and homogeneous on large scales. Yet the cosmic microwave background is not perfectly uniform. Tiny fluctuations within this relic radiation offer a window into the primordial seeds of structure formation. These minute variations foreshadow the distribution of galaxies, galaxy clusters, and the cosmic web we see today, revealing how the universe transformed from an almost featureless expanse into the intricately structured cosmos we inhabit. By studying these patterns, scientists can infer crucial details about the universe's composition, from the ratio of dark matter to ordinary matter to the influence of dark energy in driving cosmic acceleration. Beyond the observable universe and the cosmic microwave background lies the tantalizing and deeply speculative concept of the multiverse. This theory suggests that our universe is but one member of an immense ensemble of universes, each potentially governed by its own physical laws, constants, and initial conditions. These universes may coexist in higher dimensions, stacked parallel like sheets of paper, or arise continuously from mechanisms proposed in quantum mechanics and cosmic inflation. In the many worlds interpretation of quantum mechanics, every conceivable outcome of every quantum event could manifest as a new universe, leading to an almost unimaginable proliferation of realities. Meanwhile, theories rooted in string theory and eternal inflation propose a continuous generation of bubble universes, each emerging from a primordial sea of spacetime with distinct characteristics. The multiverse concept profoundly challenges our understanding of reality. If true, the laws of physics and the fundamental constants that govern matter, energy, and life might be particular to our own universe, with other universes following completely different rules. Some may resemble our universe closely, while others could be utterly alien, with environments incompatible with life as we know it. Although these ideas stretch the limits of empirical science, researchers seek indirect signatures or theoretical constraints that could lend credence to the existence of other universes. Different frameworks of the multiverse theory provide varying perspectives on cosmic multiplicity. The many worlds interpretation emphasizes branching universes resulting from quantum events, producing an infinity of parallel realities. The inflationary multiverse envisions our universe as one bubble in a vast froth of universes generated during the rapid expansion that followed the Big Bang. String theory posits a vast landscape of potential universes, potentially numbering as high as 10 to the power of 500, each defined by different laws and constants, all existing in dimensions beyond our direct perception. These scenarios offer potential explanations for the apparent fine-tuning of our universe. Out of an immense number of universes, some inevitably manifest conditions compatible with the emergence of life. The bubble universe model offers a vivid metaphor: universes as bubbles floating in a cosmic sea, forming, expanding, and perhaps even colliding with one another. During the earliest moments of creation, the inflation field drove an explosive expansion, releasing vast energy and giving rise to individual bubble universes, including the one we inhabit. This framework not only expands the boundaries of cosmology, but also challenges the philosophical notion of a single, self-contained universe, presenting a reality far more intricate and diverse than traditional models suggest. In essence, the study of cosmic expansion, the cosmic microwave background, and the multiverse interweaves observations and speculation into a narrative of the universe that is both awe-inspiring and humbling. It highlights our position as observers within a vast, dynamic, and possibly infinite cosmic arena, where the observable universe is merely a window into an ever-expanding and potentially multi-layered reality. From the red shifts of distant galaxies to the faint echoes of the early universe to the speculative realms of countless parallel universes, humanity is continually refining its understanding of the cosmos, inching closer to grasping the full grandeur of existence. However, the bubble universe hypothesis paints a picture of reality far stranger and more intricate than anything we encounter in our everyday lives. Rather than imagining cosmic inflation, the exponential expansion that followed the Big Bang, as a uniform, orderly process, this concept suggests that it may have unfolded unevenly across the fabric of space-time. Different regions of the cosmos could have expanded at divergent rates, forming discrete bubbles of reality, each inflating and evolving independently. Within each of these bubbles, the fundamental rules governing matter and energy might differ dramatically. The very constants of nature, such as the speed of light, gravitational strength, or the masses of elementary particles, could vary, and some bubbles might even harbor additional spatial dimensions entirely alien to our comprehension. This notion is as exhilarating as it is unsettling. It implies that the universe we inhabit, with its delicate balance allowing stars, planets, and life to exist, might be just one tiny bubble among an infinite sea of others, some eerily similar to ours, others so alien that life as we know it would be impossible. The bubble universe framework offers a tantalizing explanation for the apparent fine-tuning of our cosmos. We are simply observers in a universe that happens by chance to have conditions suitable for our existence, while countless other bubbles unfold under radically different laws, each with its own narrative of creation and decay. Parallel to this, the realm of quantum mechanics introduces another layer of staggering complexity to the multiverse idea through the many worlds interpretation proposed by physicist Hugh Everett in the mid-20th century. In the quantum world, particles do not follow a single predetermined path. Instead, they exist in superposition, occupying multiple states simultaneously until observed. For example, an electron can spin both up and down at the same time, only choosing one state when measured. Everett's bold insight was to suggest that all potential outcomes of every quantum event are realized, not discarded or unrealized, but in separate branching universes. Each time a particle fluctuates, a universe splits, generating a cosmic tree of infinite divergence. Every decision, every chance occurrence, even the flip of a coin, may spawn countless new realities, each hosting a version of ourselves living a life shaped by a different outcome. The implications are staggering. Imagine a universe where every possible variation of events, choices, and accidents is not hypothetical but real, coexisting silently alongside the one we perceive. These parallel worlds, while nearly identical to our own in many respects, are separated by the subtle yet absolute barriers of quantum divergence, preventing any direct interaction. We see only one thread of this infinite tapestry, yet it hints at a cosmos far richer and more complex than human intuition can easily grasp. The many worlds interpretation remains controversial, yet it forces a profound reconsideration of the very nature of reality, revealing our universe as but one filament in a vast, multidimensional weave of possibility, spun from the enigmatic behavior of subatomic particles. Beyond the branching of quantum events, the multiverse concept extends into other realms of theoretical physics, including string theory and cosmology. Some models envision our universe as one of potentially infinite membranes, or brains, drifting within a higher dimensional space. In such scenarios, universes might occasionally interact through gravitational effects or cosmic collisions, sending ripples across the cosmic ocean, detectable perhaps as anomalies in gravitational waves or subtle patterns in the cosmic microwave background, the faint afterglow of the Big Bang. Quantum entanglement, a phenomenon where particles remain mysteriously linked regardless of distance, may even provide theoretical bridges between realities, though such connections remain speculative and deeply theoretical. Wormholes, hypothesized tunnels through space-time, offer another fantastical avenue for interuniversal travel, though their existence, stability, and usability are still subjects of rigorous scientific debate. Despite the allure of these ideas, direct evidence of other universes remains elusive. Yet scientists search for indirect clues, such as anomalies in the cosmic microwave background, where unexpected cold spots or strange alignments might hint at gravitational interactions with neighboring universes. The mathematics of quantum mechanics itself, along with the sophisticated frameworks of string theory, often seem to demand the existence of multiple universes as a natural consequence. String theory, in particular, suggests that the fundamental constituents of reality are not point-like particles, but minuscule vibrating strings, each oscillation giving rise to a different particle or force. These strings are unimaginably small, tens of billions of times smaller than the nucleus of an atom, and their vibrations may require as many as 10 or 11 dimensions, most of which are compacted beyond our perception. Through this lens, the cosmos becomes an almost unfathomably intricate symphony, where the familiar four dimensions of space and time represent only a fraction of the whole. The extra dimensions may explain long-standing mysteries, such as why gravity is so much weaker than the other fundamental forces. In attempting to unify all known forces, string theory aims to produce a single coherent framework, a theory of everything, that could describe the evolution of the cosmos from the smallest quantum fluctuations to the grandest galactic structures. In this sense, both the bubble universe hypothesis and the many worlds interpretation, along with the bold conjectures of string theory, invite us to rethink reality on a scale that is profoundly disorienting and endlessly fascinating. They suggest a cosmos in which existence is not a singular, isolated event, but an intricate, almost infinite network of universes, each with its own laws, its own history, and its own version of reality. We may live in one bubble, in one branch, in one vibrating string of this colossal multiversal orchestra, but just imagining the countless others stretches the imagination to its limits, challenging everything we thought we understood about life, matter, and the cosmos itself. However, string theory continues to occupy a unique place at the frontier of modern physics, a domain where imagination, mathematics, and the limits of experimental verification intertwine. Despite decades of research, no direct experimental evidence has yet emerged to validate its predictions, leaving some critics to question whether string theory might forever remain beyond the reach of empirical testing. Yet, for many physicists and cosmologists, this very uncertainty fuels a relentless fascination, a pursuit to uncover the deepest, most elusive truths of our cosmos. String theory is not merely an abstract set of equations, it is a radical reimagining of the universe itself. Unlike our everyday experience, which is confined to 3 spatial dimensions and 1 dimension of time, string theory proposes that reality may encompass 10 or even 11 dimensions. These extra dimensions are not something we can casually observe. They are hypothesized to be compacted into scales unimaginably small, far tinier than subatomic particles, curling in ways that elude direct measurement. Yet their hidden presence could hold the key to understanding some of physics' greatest enigmas, from the elusive nature of dark matter to the long-sought unification of the fundamental forces governing the cosmos. The history of string theory's dimensionality reflects its evolving complexity. Early formulations demanded 26 dimensions, a seemingly extravagant number that was later refined to 10. Further extensions, encapsulated in what is now called M-theory, propose 11 dimensions. These extra dimensions are more than mathematical curiosities. They are thought to have genuine physical significance, potentially shaping the very structure of the universe. Unlocking their secrets is central to the quest to reconcile quantum mechanics, the theory that governs the subatomic world, and general relativity, which describes the cosmic scale of gravity. These 2 pillars of physics, so successful in their respective realms, have resisted unification for over a century, and string theory offers one of the few coherent frameworks that might finally bridge the divide. Within this framework, the concept of brains, short for membranes, emerges as a fundamental building block of reality. Brains are multidimensional surfaces that can extend across space and time, existing in dimensions beyond our perception. Our universe, according to string theory, might itself be a 3-dimensional brain floating in a higher dimensional expanse known as the bulk. This bulk could host countless other brains, each potentially representing a distinct universe, a multiverse in which parallel realities coexist, separated by dimensions that remain imperceptible to us. The implications of brains stretch far beyond mere abstraction. They suggest that the universe we inhabit may be only one of many, each governed by its own physical laws, constants, or even dimensional structures. Interactions between brains might account for some of the most dramatic cosmic events. For instance, certain hypotheses posit that the Big Bang, the explosive origin of our universe, could have resulted from the collision of two brains within this higher dimensional space. Such scenarios offer a profoundly new lens through which to view the birth, evolution, and ultimate fate of our universe, suggesting that reality is far more intricate and expansive than our senses can grasp. The nature of extra dimensions itself is a subject of remarkable variety. Some may be infinitesimally small, compacted into tight loops that are undetectable to even the most precise instruments. To visualize this, imagine a tightrope stretched across a vast landscape. From afar, it seems like a simple one-dimensional line, yet upon closer inspection, an ant could traverse around the circumference, experiencing an extra dimension hidden from human eyes. Other dimensions could be vast, yet fundamentally inaccessible, analogous to a two-dimensional being inhabiting a flat plane who has no concept of height. In this scenario, our four-dimensional perception, the three spatial dimensions plus time, could be a limited slice of a far grander, more intricate reality. Yet another possibility is that extra dimensions are separated from our familiar universe by tremendous amounts of energy, effectively isolating them from matter and light. In such cases, these hidden dimensions might be as real as the world we perceive, yet forever invisible under ordinary conditions. Even more intriguingly, evidence of extra dimensions could be all around us, imperceptible simply because our brains and senses evolved to interpret only a four-dimensional universe. Much like a person who is colorblind cannot see certain shades of red or green, we may be blind to facets of reality that lie just beyond the threshold of human cognition. M-theory represents the most ambitious synthesis of these ideas, unifying various strands of string theory into a single coherent framework. Expanding upon previous models that propose 10 dimensions, M-theory posits 11 dimensions and envisions the universe as composed not of point-like particles, but of vibrating one-dimensional strings. These strings oscillate in complex ways, giving rise to the diversity of particles and forces that constitute the observable universe. The theory further incorporates multidimensional brains, suggesting that these membranes are not static backdrops, but dynamic entities that can influence the evolution of entire universes, potentially giving rise to the complex multiverse of realities suggested by modern theoretical physics. In this sense, string theory and extension, M-theory, offers not just a mathematical model, but a sweeping visionary framework for understanding the cosmos. It challenges the boundaries of human imagination and compels us to consider a universe that is vastly richer and stranger than our senses reveal. While experimental proof remains elusive, the journey to explore these hidden dimensions, to uncover the vibrations of fundamental strings, and to map the brains that might cradle entire universes continues to inspire some of the most brilliant minds in science, pushing the frontier of what it means to understand reality itself. One of the most compelling and intellectually tantalizing aspects of theory lies in its bold ambition to reconcile two of the most successful, yet seemingly incompatible frameworks in modern physics: quantum mechanics, which governs the subatomic realm, and general relativity, which dictates the behavior of massive objects and the curvature of spacetime. For decades, these two pillars have resisted unification, with quantum mechanics flourishing in the microscopic world of particles and fields, while general relativity reigns supreme on cosmic scales, describing stars, galaxies, and the expansion of the universe itself. M-theory, however, proposes a radical vision that, at a fundamental level, all forces and particles may be manifestations of a single underlying reality, governed by the intricate mathematics of higher dimensional objects known as brains and tiny, vibrating strings. In offering a unified description of the four fundamental forces, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, M-theory stands as a candidate for the long-sought theory of everything, a goal that has captured the imagination of physicists for generations. Despite its elegance, M-theory remains highly speculative, resting largely on theoretical consistency rather than experimental confirmation. Yet its capacity to illuminate the deepest mysteries of the cosmos continues to enthrall scientists, inspiring new approaches to age-old questions about the nature of reality. The promise of M-theory lies not merely in mathematical beauty, but in its potential to predict phenomena that could bridge the chasm between the observable and the theoretical. As researchers labor to extract testable predictions from its framework, M-theory occupies a central position in the ongoing quest to understand the fabric of the universe, pushing the boundaries of knowledge and challenging us to expand our conceptual horizons. A particularly mesmerizing feature of this theoretical landscape is the concept of extra dimensions, hidden spatial directions beyond the three we perceive, along with the familiar dimension of time. While human perception confines us to length, width, height, and the progression of time, some theories suggest that additional dimensions may exist, compactified so tightly that they evade direct detection. These extra dimensions might hold the key to a profound mystery, the apparent weakness of gravity compared to other fundamental forces. Rather than being inherently feeble, gravity may simply disperse across these unseen dimensions, leaving only a fraction of its full strength detectable within our familiar four-dimensional spacetime. Such a revelation would not only redefine our understanding of gravity, but also provide a bridge to the other forces, unifying them under a common framework consistent with string theory. String theory, the conceptual bedrock of M-theory, envisions all matter and forces as emerging from infinitesimal, vibrating strings of energy. These strings, like the resonant strings of a cosmic instrument, require extra dimensions to vibrate in specific ways, giving rise to the diversity of particles and forces that compose our universe. If these dimensions exist, they could fundamentally alter our understanding of phenomena such as dark matter and dark energy, enigmatic components of the cosmos whose influence is palpable yet whose nature remains largely invisible. The hidden dimensions may also shape the formation and behavior of black holes, guiding the very evolution of galaxies and the large-scale structure of the universe. By extending our perspective beyond the perceptible four dimensions, physicists hope to uncover a richer, more complete picture of reality itself. To detect these elusive dimensions, scientists employ an array of ingenious experimental techniques. Particle accelerators, such as the Large Hadron Collider at CERN, propel particles to staggering energies and collide them in hopes of glimpsing signs of extra dimensions. If particles momentarily escape into these hidden realms, the missing energy could leave subtle yet detectable traces in the intricate detectors surrounding the collision points. Other approaches investigate gravity on minuscule scales, using ultra-sensitive instruments to measure forces between objects separated by tiny distances, searching for deviations that might betray the influence of unseen dimensions. Astronomers complement these efforts by probing the cosmic microwave background, the faint afterglow of the Big Bang, for subtle irregularities that could hint at the presence of additional spatial dimensions in the infant universe. Black holes and the expansion of space itself also offer tantalizing observational avenues, with researchers examining whether their properties bear fingerprints of higher dimensions. Collectively, these efforts illustrate the creativity and persistence of the scientific community in its relentless pursuit of the universe's hidden architecture. Even without definitive evidence yet, the implications of discovering extra dimensions are staggering. They could provide a framework for parallel universes, suggesting that reality is far broader and more intricate than our immediate experience conveys. Such dimensions might exist alongside our known spatial and temporal directions, folded into compact configurations that evade detection but nonetheless govern fundamental processes. If proven, these dimensions could explain the invisible scaffolding behind dark matter and dark energy, or even offer connections to other universes, hinting at a vast multiverse where distinct realms obey their own physical laws. The revelation of extra dimensions would not merely expand our understanding of the cosmos, it would fundamentally challenge our conception of existence itself, showing that the universe is far more intricate and layered than previously imagined. Equally profound is the question of whether the universe has an edge. Cosmologists generally conclude that the universe lacks a conventional boundary. Observations indicate that space itself is expanding, with every point moving away from every other point, not within a pre-existing void, but through the stretching of spacetime itself. From our vantage, the universe appears remarkably uniform, obeying the same physical laws across vast cosmic distances. If the universe is infinite, then the notion of an edge is meaningless. It extends endlessly in all directions. Conversely, if the universe is finite, it may possess a curved geometry akin to the surface of a sphere, in which traveling straight in one direction would eventually return you to your starting point, analogous to circumnavigating Earth. When scientists discuss the edge of the universe, they refer not to a physical boundary, but to the limits of the observable universe, the farthest distances from which light has traveled to reach us in nearly 14 billion years. Beyond this horizon, we cannot directly observe, though it does not imply nothing exists there. The concept becomes even more intricate when considering the universe's potential curvature or infinite extent. Advanced observational techniques and increasingly sensitive instruments may eventually extend the limits of the observable universe, revealing new structures and phenomena beyond our current cosmic horizon. In this way, the interplay between theory and observation continues to shape our understanding, challenging our perception of space, time, and the very nature of reality. From the mysterious vibrations of strings to the hidden folds of extra dimensions and the elusive boundaries of space, the ongoing quest to comprehend the universe exemplifies human curiosity at its most audacious. Every theoretical insight and experimental endeavor brings us closer to a profound truth: that reality in all its complexity extends far beyond what the senses reveal, inviting us to explore, question, and marvel at the grandeur of the cosmos. However, due to the relentless expansion of space itself, there will always be regions that drift beyond our view, areas retreating faster than light could ever travel, slipping forever out of reach. It's a strange truth. While nothing can move through space faster than light, the fabric of space itself can stretch at any rate, carrying galaxies along like leaves on an ever-widening river. The universe, in its grand expansion, confronts us with a paradox that challenges our deepest intuitions. When we ask about its edge, we imagine a border, a wall, perhaps, or a vast emptiness waiting beyond. But the universe has no edge, at least not in any way that resembles a frontier. It isn't expanding into something. Rather, it's creating space itself, everywhere, all the time. Each instant, new distance is born between galaxies, between stars, between us and everything else. Picture a loaf of raisin bread rising in an oven. As the dough swells, every raisin moves away from every other. Yet there's no special center, no outer crust that marks the edge of everything. The universe behaves the same way. Wherever you stand, whether on Earth, in a distant galaxy, or in some remote corner of cosmic emptiness, you will see other galaxies racing away from you in all directions. Every observer, no matter their location, perceives themselves as being at the center of expansion. That is the nature of space itself, uniform, unbounded, and alive with motion. When we speak of the edge of the universe, we're usually referring to something else entirely, the edge of the observable universe. This boundary isn't a wall or a rim, but a limit imposed by light and time. Because the universe has a finite age, roughly 13.8 billion years, we can only see as far as light has had time to travel since the Big Bang. Beyond that horizon lies a vast, unseen realm, still expanding, still creating new distances, regions that may never come within our reach. And yet, beyond this invisible curtain, the universe likely continues, stretching endlessly. The galaxies that we see are but a fraction of what exists. There could be countless more, billions upon billions of them, scattered across the unseen expanse, each a cosmic city of stars, planets, and perhaps life. Some cosmologists believe that what lies beyond is remarkably similar to what we observe here. More clusters, more filaments, more islands of light adrift in the cosmic sea. But others suggest something far stranger. The multiverse hypothesis proposes that our universe might be just one of many. A single bubble in a vast cosmic foam, each bubble with its own laws of physics, its own constants, perhaps even its own dimensions of space and time. These parallel realms, if they exist, may be forever sealed from us by barriers we cannot cross, their presence detectable only through faint mathematical whispers. And there are theories that go even deeper, proposing that beyond our horizon, the very fabric of reality could change. The forces that hold atoms together, the nature of light, even the flow of time itself might differ in distant regions where the rules we know begin to falter. Our observable universe may just be one patch of a much grander, more complex whole, an island of familiar physics adrift in a cosmic archipelago of the unknown. The leading cosmological model today, known as the lambda cold dark matter model, paints a picture of a universe that is both simple and awe-inspiring. It suggests that what we can see, the galaxies, the stars, the faint cosmic background radiation, is only a small portion of a much larger, possibly infinite expanse. Space, according to this view, has no boundary. It simply stretches without end. The only limits are those imposed by the speed of light and the age of everything. Yet other models envision a finite universe with a specific shape, perhaps a vast three-dimensional sphere that wraps back on itself, or a more exotic form like a 12-sided dodecahedron. In such a cosmos, traveling far enough in one direction might eventually bring you back to where you started, just as a sailor might circle the Earth and return to their own port. Some interpretations of string theory take an even bolder approach, imagining our universe as just one membrane, one brain, floating in a higher dimensional space, surrounded by countless others. But whatever the shape or scope, when cosmologists speak of the edge of the universe, they are not referring to a cliff at the end of existence. They speak instead of the horizon of our knowledge, the limits of what light has shown us so far. Beyond that horizon, the story of the cosmos continues, unwritten and unseen. To understand that grand story, scientists look to the largest known structure in existence, the cosmic web. This is the universe's skeleton, a vast interconnected network of filaments stretching across billions of light years. Within these filaments, galaxies cluster like luminous beads strung along invisible threads. Between them yawns a darkness so deep and wide that it dwarfs any notion of emptiness we can comprehend. Imagine this web as an enormous three-dimensional spider's web spanning the observable universe. The filaments are made primarily of dark matter, an invisible substance that neither emits nor reflects light, yet outweighs all visible matter by a factor of about 5 to 1. Though unseen, its gravity sculpts the cosmos, drawing gas, dust, and stars into the shapes we observe today. Galaxies, in turn, gather at the intersections of these filaments, forming immense clusters, cosmic metropolises bound together by gravity. Between them lie immense voids, vast and nearly empty, the silent deserts of the universe. These voids and filaments tell the story of the universe's growth. In the beginning, mere fractions of a second after the Big Bang, the universe was almost perfectly smooth, with only tiny fluctuations in density. Over billions of years, gravity amplified those fluctuations, pulling matter together to form filaments and leaving behind enormous voids. Today, this intricate pattern is the cosmic fingerprint of everything that has happened since time began. By mapping these structures, astronomers can trace how matter is distributed, how dark energy drives the accelerating expansion of space, and how the universe might continue to evolve. Each filament, each void, is a clue, a piece of evidence in the grand investigation of our cosmic origins. Dark matter, though invisible, remains the architect of it all. Accounting for about 85% of the universe's total matter, it shapes the gravitational scaffolding upon which everything else is built. Galaxies form and spin within halos of this unseen material, their motions dictated by its pull. Even beyond visible galaxies, dark matter's reach continues, its gravity binding clusters into superclusters, threading the web that connects all things. Its influence blurs the lines between cosmic structures. The halos of dark matter surrounding galaxies and clusters extend so far that they often overlap, creating a seamless gravitational continuum. In this way, the cosmos is less a collection of isolated islands and more a vast, interconnected ocean of matter and energy. And so, the question of boundaries, the edge of everything, remains as elusive as ever. The universe may be infinite, or it may curve back upon itself. It may be one of many, or it may stand alone. But no matter the model, one truth persists. The horizon we see is not the end. It is a mirror reflecting the limits of our vision, a reminder that beyond the farthest galaxy we can detect lies an eternity still waiting to be discovered. Furthermore, dark matter stands as one of the most mysterious and influential components of our universe, silently shaping the grand architecture of the cosmos. It does not emit or absorb light, and yet its gravitational pull governs the movement of galaxies, binds clusters together, and determines how matter is distributed on the largest scales imaginable. This invisible substance has become central to our ongoing debates about the universe's overall geometry and the question of whether the cosmos has any definable edge or boundary. The amount and spread of dark matter affect how we calculate the universe's total mass and energy, measurements that directly inform our understanding of cosmic expansion and the universe's possible destinies. Every refinement in our knowledge of dark matter brings scientists a step closer to answering profound questions about what kind of universe we inhabit, how it began, and how it might one day end. And yet, even as we probe the shadows cast by this unseen matter, we are confronted with a question that stretches imagination to its breaking point. Could the universe itself be infinite? The idea is as humbling as it is unsettling. When cosmologists speak of an infinite universe, they mean a cosmos that extends endlessly in every direction. No walls, no outer rim, no final frontier where space simply ceases to exist. No matter how far we might travel, there would always be more space, more stars, more galaxies lying beyond the horizon of our vision. Such a concept implies a reality so vast that the part we can observe, the billions of galaxies mapped by our telescopes, would represent only an infinitesimal fraction of all that exists. Our so-called observable universe, enormous as it seems, would be little more than a tiny bubble floating within a limitless sea of space and time. This notion challenges not just our scientific frameworks, but our very sense of existence. Infinity in the context of the universe is not a simple idea of a lot, but a mind-bending state of without end. It forces us to question the nature of boundaries, measurement, and even meaning itself. If space truly goes on forever, does that mean matter also repeats infinitely? Could there be countless copies of our galaxy, or of ourselves, spread across an infinite expanse? Most cosmologists caution against such literal interpretations. Infinity, they remind us, does not necessarily imply endless repetition or every conceivable arrangement of matter. Rather, it signifies a universe with no terminus, an eternal canvas upon which cosmic structures continue to emerge, evolve, and vanish without limit. Still, infinity is not the only possibility. Some scientists propose that the universe may be finite but unbounded, a concept that defies intuition but holds deep mathematical beauty. Imagine for a moment the surface of the Earth. You can travel in any direction indefinitely without ever encountering an edge, yet the Earth's surface area is finite. Now extend that idea into three-dimensional space. A finite but unbounded universe would operate on a similar principle. You could journey through it endlessly and eventually return to your starting point, never encountering a boundary, even though the total volume of the cosmos remains limited. This kind of universe, unlike an infinite one, would possess a subtle curvature, folding space back upon itself in higher dimensions. The curvature would be so gradual that it would be imperceptible across human or even galactic scales, becoming noticeable only when measured across cosmic distances. The geometry of space plays a decisive role in these models. In an infinite universe, space would likely be flat or open, stretching forever without looping back. A finite but unbounded universe, on the other hand, would exhibit a closed curved geometry, like the surface of a sphere extended into higher dimensions. These differing shapes lead to very different implications for the total amount of matter and energy that exists. An infinite universe would contain an infinite quantity of both, while a finite but unbounded one would hold a vast yet countable amount of matter and energy. Such distinctions might seem abstract, but they determine how galaxies form, how gravity behaves on colossal scales, and ultimately, how the universe might evolve or cease to exist. The idea of an infinite cosmos has captivated thinkers for centuries, from ancient philosophers who pondered the endless heavens to modern cosmologists armed with satellites and supercomputers. The evidence we have gathered paints a complex and sometimes contradictory picture. Observations of the cosmic microwave background, the faint afterglow of the Big Bang, indicate that the universe appears remarkably flat on large scales. In many theoretical models, a perfectly flat universe is one that extends infinitely. Yet this observation is not proof of infinity. It merely shows that, within the limits of what we can see, space does not appear to curve significantly. Beyond that horizon, the cosmic boundary defined by the distance light has traveled since the universe began. We cannot observe directly. What lies beyond remains pure speculation, hidden from view not by technology, but by the fundamental structure of space-time itself. Adding to the mystery is the theory of cosmic inflation, According to this idea, in the first fractions of a second after the Big Bang, the universe expanded exponentially, growing from subatomic scales to cosmic dimensions almost instantly. Some versions of inflationary theory suggest that this expansion might never have completely stopped. If true, our observable universe could be just one bubble among countless others within a vast multiverse, a cosmic foam of universes, each potentially governed by different physical laws. In that case, the total cosmos might be finite in some regions and infinite in others, an intricate mosaic of realities extending far beyond what we can ever perceive. Every discovery in cosmology, every refinement of our measurements, brings us a little closer to understanding the true nature of the universe. Yet with each answer comes a deeper, more profound question. Whether the cosmos is infinite or merely immense beyond imagination, whether it will expand forever or one day fold back upon itself, the search continues. It is a pursuit that reflects both our intellectual curiosity and our deep human need to understand our place within the vast, silent expanse that surrounds us. And yet, even as we gaze into the night sky, we find ourselves confronted by a mystery so vast that human language strains to contain it. The observable universe, what our telescopes and instruments can detect, is staggeringly immense, stretching across billions of light years. But beyond that faint horizon, beyond the limit imposed by the finite speed of light and the age of the cosmos, lies a question that has haunted astronomers and philosophers alike. Is the universe truly infinite or merely unimaginably large? Some scientists suggest that the remarkable uniformity of the cosmos, its apparent sameness in every direction, might not require infinity to explain. Perhaps the universe is finite, but so enormous that to us it appears boundless. Picture a cosmic ocean extending farther than any probe could ever travel, yet ultimately curving back upon itself, looping endlessly like the surface of a sphere. In such a universe, one could, in theory, travel forever without ever finding an edge. But infinity, in the language of cosmology, is not just a mathematical curiosity. It is a challenge to everything we think we understand about space, time, and existence itself. If space is infinite, then no matter how far we journey, there is always more. No boundary, no center, no outer rim where the cosmos ends and something else begins. And if time, too, is infinite, then what of beginnings and endings? Some theories imagine that time stretches backward without limit, that there was never a first moment. Others suggest that while the universe had a beginning, its expansion will continue endlessly into the future, pushing galaxies farther and farther apart until even their light fades into darkness. Still, infinity brings with it a deep unease. The universe we can observe is finite, defined by the distance light has been able to travel since the Big Bang roughly 13.5 billion years ago. Beyond that, the nature of space and time becomes speculative territory, a vast unknown that tempts human imagination but defies confirmation. And it is within this uncertainty that some of the most mind-expanding ideas in modern physics arise: the multiverse, the cyclic universe, the steady-state model, and the concept of eternal inflation. The idea of infinity in cosmology touches on something profoundly human: our longing to understand what lies beyond. The notion that there might be infinite copies of Earth, or even infinite versions of ourselves, has captured both scientific and philosophical imagination. But an infinite universe does not guarantee infinite repetition. Even if the cosmos extends forever and matter is spread relatively evenly across it, the odds of recreating the exact same planet with the same people, histories, and choices are vanishingly small. The universe is governed by chaotic processes and quantum uncertainties that make perfect duplication nearly impossible. In an infinite expanse, there might be countless Earth-like worlds, some eerily similar, others utterly alien, but each would have its own story, its own thread in the endless cosmic tapestry. And then there are the theories that take infinity to heart. Some physicists have proposed that the universe never truly began and will never truly end. The steady-state model, once popular in the mid-20th century, imagined a cosmos eternally expanding, yet remaining unchanged, with new matter continually forming to fill the gaps. Though largely set aside after the discovery of cosmic microwave background radiation, evidence supporting the Big Bang, it was an early attempt to escape the troubling question of a singular origin. Newer theories, like the cyclic model, envision an eternal rhythm of creation and destruction, expansion followed by contraction, birth followed by collapse. Each big crunch gives rise to a new Big Bang, erasing what came before and beginning again. In these models, the universe is a self-renewing system without a true beginning or end, an infinite heartbeat pulsing across the ages. And within the vast frameworks of string theory and quantum gravity, some versions of the multiverse take this even further, proposing an infinite collection of universes, each governed by its own physical laws, each endlessly generating new realities. Infinity, however, is not without paradox. If the universe truly extends forever, then everything that can happen must happen. Not once, but infinitely many times. Somewhere, perhaps an unthinkable distance away, there could exist another you reading this same sentence, making slightly different choices, living a slightly different life. And if matter and energy are infinite, why does the universe appear so uniform, so delicately balanced? Why do we not see infinitely dense regions or endless cosmic structures? There is also the puzzle of entropy. In an infinite universe existing for infinite time, one might expect all energy to have dispersed evenly, resulting in a cold, lifeless void, a cosmic heat death. Yet we find ourselves in a dynamic, structured universe filled with galaxies, stars, and life. How can that be if infinity should have already run its course? The answers remain elusive, reminding us that even our best theories are fragments of a much larger truth we are still far from grasping. And then, as if to deepen the mystery, comes the idea of cosmic inflation. In the earliest fractions of a second after the Big Bang, according to this theory, the universe expanded exponentially, faster than light itself, smoothing out irregularities and setting the stage for everything that followed. But what if that inflation never ended everywhere? Some regions might have stopped expanding, giving rise to universes like ours, while others continued indefinitely, spawning new bubble universes in a process called eternal inflation. If this is true, then our observable cosmos is merely one pocket in a grand infinite multiverse, an island of light in a sea without end. And so, as we look into the depths of space, what we see is both humbling and exhilarating. The question of infinity is not just about the scale of the universe, it is about the limits of our own comprehension. Each theory, each observation pushes those limits a little farther, urging us to imagine realities beyond our senses. Whether the universe is finite or infinite, it confronts us with a profound truth. We are part of something far larger than ourselves, something that stretches beyond the horizon of thought, perhaps even beyond the reach of time itself. However, it is important to recognize that while the theory of cosmic inflation stands as one of the most successful and well-supported ideas in modern cosmology, the notion of an infinite universe, or even more boldly, a multiverse, remains perched on the edge of speculation. The observable universe, vast as it may seem, is merely a small island in a cosmic ocean whose true expanse we may never measure. Our instruments, however advanced, are limited by the speed of light and the age of the cosmos itself. Beyond that cosmic horizon, we cannot see, we cannot test, and we can only imagine. Yet it is within these unreachable realms that some of the most daring scientific ideas of our time find their home. Cosmic inflation is a theory that attempts to describe the universe's earliest heartbeat, a fleeting, unimaginably small moment after the Big Bang, when space itself expanded at an extraordinary rate. In less than a trillionth of a second, the universe grew exponentially, expanding faster than the speed of light. Not because anything moved through space that quickly, but because space itself stretched. This sudden surge of expansion smoothed out any irregularities that might have existed in the infant cosmos, leaving behind a universe that appears remarkably uniform in every direction we look. It also laid the groundwork for the cosmic web of galaxies, clusters, and filaments that would later emerge as the universe cooled and matter began to clump together. But inflation might have done more than just set the stage for our own universe. Some versions of the theory propose that the process did not stop everywhere at once. Instead, while inflation ceased in our region, allowing energy to condense into matter, stars, and galaxies, it may have continued in distant regions of space, endlessly spawning new bubble universes. This concept, known as eternal inflation, paints a breathtaking picture, A vast, ever-growing froth of universes, each bubble an entire cosmos unto itself, each potentially governed by its own physical laws and constants. Our universe, in this view, is but one bubble in an infinite cosmic sea. Imagine a landscape of expanding space-time, a boundless field of quantum energy constantly giving birth to new realms. In this endless inflationary expanse, each bubble universe begins as a tiny fluctuation, an energetic spark that swells and stabilizes, forming its own unique reality. Some bubbles might mirror our own, filled with galaxies, stars, and life. Others might be profoundly alien, perhaps lacking the chemistry needed for atoms to form, or existing in more or fewer dimensions than the four we perceive. Between these universes, the space continues to inflate, driving them ever farther apart, so distant from one another that they could never collide or communicate. The bubble universe model offers a possible answer to one of the great cosmic puzzles, the fine-tuning of our universe. Why do the laws of physics seem so precisely calibrated for life? The multiverse provides a provocative alternative to the idea of design or sheer coincidence. If countless universes exist, each with different laws and constants, then it is not surprising that at least one would have conditions suitable for life, and that we find ourselves in it. In another bubble, gravity might be far stronger, crushing stars before they can stabilize. In yet another, the electromagnetic force might be weaker, preventing atoms from binding together. Some universes might expand too fast for galaxies to form, others might collapse before stars ever ignite. And then there is string theory, another pillar of theoretical physics, that adds yet another layer to this grand vision. String theory suggests that what we perceive as particles are, in fact, tiny vibrating strings of energy, and that these strings can exist in multiple configurations, each giving rise to different kinds of physical realities. The theory predicts an almost unfathomable landscape of possible universes, on the order of 10 to the power of 500. Each universe would correspond to a different solution to the equations of string theory, with its own values for the fundamental constants, its own number of dimensions, and its own cosmic architecture. Our universe, according to this view, is simply one particular solution, a single valley in a vast and incomprehensible topography of possible realities. This brings us to a profound philosophical question. Why this universe? Why do we find ourselves in a cosmos where matter can form, where stars can shine, and where conscious beings can ask such questions? Here, the anthropic principle comes into play. It suggests that we observe the universe the way it is, precisely because only such a universe can give rise to observers like us. Within the framework of the multiverse, this principle takes on powerful meaning. Out of an infinite variety of universes, we inhabit the one where conditions allow life to emerge and evolve. We should not be surprised that our universe seems fine-tuned. It is the only kind we could ever experience. Yet, not all scientists are convinced. The multiverse, as elegant and sweeping as it may sound, teeters on the edge of what can be considered science. The chief criticism is that these other universes, by their very nature, lie beyond observation. If we can never detect them, if no signal, no light, no evidence can ever reach us from beyond our cosmic horizon, then how can we claim they exist? Some argue that this makes the multiverse untestable and therefore unscientific. Others counter that while direct evidence may be impossible, indirect traces, such as subtle imprints on the cosmic microwave background, could one day provide support for the theory. There are also deeper philosophical concerns. If our universe arose from a larger multiverse, what created the multiverse itself? Does the chain of creation stretch back infinitely, or is there an ultimate origin beyond even this grand ensemble of worlds? These questions push the boundaries of cosmology into the realm of metaphysics. Furthermore, the use of probability in an infinite multiverse poses its own challenges. How can we meaningfully discuss likelihoods when dealing with infinite sets of universes, each with its own rules and constants? Despite these debates, the allure of the multiverse endures. It represents both a scientific hypothesis and a profound shift in perspective, a recognition that our universe might not be the whole story, but just one chapter in an infinite cosmic saga. If true, the multiverse would form our understanding of existence itself. It would mean that everything we know, every galaxy, every atom, every moment, exists within a single bubble, adrift in a boundless cosmic ocean, forever expanding, forever creating, forever beyond our reach. However, scientists are not content with speculation alone. Across the world, they are developing ingenious methods to probe the very edges of our understanding, seeking evidence that might confirm or completely overturn the most daring cosmological theories ever proposed. One of the most promising approaches lies in the study of the cosmic microwave background, the faint afterglow left behind from the earliest moments of the universe's existence. This ancient light, still washing over us from every direction, carries within it subtle ripples, temperature fluctuations, and patterns of polarization that act like fingerprints of the cosmos's birth. If our universe had ever brushed against another during its infancy, that cosmic encounter could have imprinted barely perceptible distortions into this background radiation. Scientists pore over immense datasets gathered by advanced telescopes, satellites orbiting high above Earth, cooled to near absolute zero, to detect these faint signals. They search for strange circular patterns or temperature anomalies that might hint at a cosmic collision, a scar left by another universe pressing against our own. Each new layer of analysis brings them closer to distinguishing between ordinary cosmic noise and a signature that might reveal a far deeper truth. Another line of investigation turns its gaze toward the grand architecture of the cosmos itself, the vast web of galaxies that stretches across billions of light years. Inflationary models of the multiverse predict that the distribution of galaxies should follow certain mathematical patterns, subtle symmetries imprinted during the universe's earliest moments of inflation. Astronomers map these colossal structures using massive sky surveys, tracing the filaments and voids of the cosmic web. Every new galaxy catalog adds to a growing, intricate puzzle, one that might one day confirm that our universe's structure was shaped not only by its own internal forces, but also by influences from beyond its boundaries. And then there are the whispers of space-time itself, gravitational waves. These ripples, first detected in 2015, have opened an entirely new window onto the universe. Some theorists believe that collisions between entire universes, or violent events during the rapid inflationary period, could have generated distinctive gravitational wave patterns. Future detectors, operating on the ground and in the quiet of space, might one day be sensitive enough to catch these faint tremors, echoes not from exploding stars or merging black holes, but from the birth of universes themselves. Among the most audacious ideas to emerge from modern physics is brain cosmology, a concept that challenges even the most fundamental assumptions about space and time. In this framework, our universe is not all that exists. It is merely a three-dimensional membrane, or brain, floating within a higher dimensional arena known as the bulk. Everything we experience, light, matter, and the familiar forces of nature, is confined to our brain. Only gravity, elusive and weak, can seep beyond these confines, moving freely through the extra dimensions of the bulk. This might explain why gravity feels so much weaker than the other fundamental forces. It is not weak by nature, but diluted, spread across dimensions we cannot perceive. The implications of this theory are staggering. If multiple brains exist within the bulk, then there could be other universes, parallel realities, just millimeters away in an unseen direction. Each of these universes might have its own laws of physics, its own constants, even its own forms of matter and energy. The bulk itself could possess more than 4 dimensions, perhaps 10 or 11, far beyond our ability to visualize. In this grander picture, gravity becomes a cosmic messenger, whispering between worlds. It could even reveal why our universe behaves the way it does. Some versions of brain theory propose that the Big Bang was not the beginning of everything, but rather the aftermath of a collision between two brains. When they crashed together, the immense energy released might have ignited the creation of matter, space, and time as we know them. Our cosmos, then, would not have emerged from a single point of infinite density, but from a titanic interaction within a higher dimensional realm. The concept of the bulk, this vast, unseen expanse beyond our familiar space-time, continues to captivate theorists. It serves as the hidden stage upon which all universes might coexist. Gravity could be leaking into this higher dimensional backdrop, offering a tantalizing explanation for why it is so weak compared to electromagnetism or the nuclear forces. Some researchers even speculate that dark matter and dark energy, Those mysterious entities making up most of the universe's mass and energy might be the shadows or effects of interactions between our brain and others drifting through the bulk. If these ideas hold true, then our universe is not the totality of existence. It is a small part of a boundless, multidimensional cosmos where collisions and interactions give birth to new worlds. Brain collisions, in particular, present a spectacular reimagining of creation itself. Picture two immense, invisible sheets of reality floating through a higher dimensional ocean. For eons, they drift apart in silence. Then, as they finally touch, unimaginable energy bursts forth, energy enough to form stars, galaxies, and the fabric of time itself. What we call the Big Bang could be just one such collision, one heartbeat in a much larger cosmic cycle. While these ideas remain highly speculative, they represent humanity's relentless drive to understand the ultimate questions. Where did we come from? Why does the universe exist at all? And might there be others, vast and hidden, existing beside our own? In laboratories and observatories, on whiteboards filled with equations and computers processing endless streams of cosmic data, scientists continue the search. Each observation, each refinement of theory, brings us a fraction closer to glimpsing the full structure of the cosmos, an intricate, multidimensional symphony that may extend far beyond the boundaries of imagination. However, detecting any tangible evidence of other brains or of the colossal collisions between them remains one of the most profound challenges facing modern physics. Instruments of extraordinary sensitivity probe the deepest corners of space, yet the traces of these grand encounters, if they exist, lie hidden behind the veil of the cosmos. And yet, a daring theoretical framework, known as the ekpyrotic or fiery birth universe model, dares to tell a very different story of our cosmic origin. Instead of a sudden, singular explosion, a Big Bang bursting from nothing, this idea envisions the beginning as the slow, majestic dance of two enormous, flat membranes drifting through a higher dimensional space. These membranes, or brains, glide within a vast, invisible realm possessing more dimensions than the three of space and the one of time that we perceive. Over unimaginable stretches of time, these brains drift, ripple, and occasionally collide. When such a collision occurs, the energy released in that moment, immense beyond comprehension, could ignite an entire universe. One of those impacts, the theory suggests, may have given birth to ours. In this vision, our universe is not the totality of existence, but rather a shimmering three-dimensional sheet floating upon a higher dimensional bulk. This framework, called brain cosmology, emerges from string theory, the proposal that all matter and forces originate not from point-like particles, but from tiny vibrating strings of energy. Through this lens, every atom, every star, and every galaxy is but a vibration upon this cosmic membrane. The ekpyrotic model was conceived to resolve some of the lingering puzzles of the traditional Big Bang. It offers natural explanations for why the cosmic microwave background, the faint afterglow of the early universe, appears so uniform in every direction, and why space itself seems so flat. In the conventional model, these features require a brief but extreme burst of inflation, a period when the universe expanded faster than the speed of light. The ekpyrotic universe, however, proposes that these same characteristics arise naturally from the geometry and dynamics of the brain collision itself. One of the most perplexing mysteries in modern physics is the hierarchy problem. Why gravity, the force that binds planets and galaxies, appears so weak compared to the other fundamental forces. Brain cosmology offers an elegant possibility. If gravity can leak into extra dimensions, flowing freely through the higher dimensional bulk, its apparent weakness in our world might simply be an illusion. The other forces, such as electromagnetism and the strong and weak nuclear forces, remain confined to our three-dimensional brain, while gravity diffuses through the higher dimensional space, losing strength as it spreads. This could mean that on a deeper level, gravity is just as strong as the others. It merely hides its true power across unseen dimensions. Such an idea transforms the way we understand the universe. If extra dimensions truly exist, then what we perceive as the universe might be only a small fraction of a much grander reality. The faint pull of gravity across the cosmos could be whispering to us from beyond our own brain, echoing through the unseen bulk. Scientists have sought possible clues to test these bold theories. One possibility lies in gravitational waves, the ripples in space-time first directly detected in 2015. If gravity indeed spreads through extra dimensions, then some waves might behave differently than predicted by Einstein's general relativity. They could appear with unusual frequencies or amplitudes, slight distortions that betray their passage through hidden realms. Future generations of detectors, far more sensitive than those we possess today, may one day catch such signatures. Another line of investigation comes from studying gravity itself over immense distances. If brain cosmology is correct, gravity might subtly weaken or strengthen across cosmic scales, deviating from the neat inverse square law that holds locally. Observations of the motions of galaxies, the growth of cosmic structures, or the rate of the universe's expansion could reveal these delicate differences. Even the ancient cosmic microwave background, the faint radiation still glowing from the birth of the cosmos, might bear the fingerprints of a brain collision. Tiny irregularities or unusual temperature patterns across this background could hint at a past encounter between our universe and another. Such a discovery would shake the foundations of physics, suggesting that our cosmic history began not in isolation, but in a vast, multidimensional interplay of universes. Brain cosmology departs radically from the classical Big Bang model. In the traditional picture, everything, space, time, energy, and matter, emerges from an infinitesimal singularity that suddenly expands. In the brain perspective, the beginning is not a point but an event, a collision between two immense sheets floating in higher dimensional space. This replaces the singularity, potentially resolving many of the infinite quantities and paradoxes that have long troubled cosmologists. Furthermore, this vision naturally accommodates the idea of parallel universes. If other brains exist, each could host its own universe, its own stars, galaxies, perhaps even life, unseen and unreachable to us, separated only by the thin barrier of extra-dimensional space. It is a concept both humbling and exhilarating. Our cosmos may be one among countless others, all drifting in an endless, multidimensional sea. Extending this concept even further, some physicists have proposed a cyclic universe, a cosmos that undergoes endless cycles of expansion and contraction. In such a model, each collision between brains triggers a new Big Bang, creating a new universe in a repeating pattern without a true beginning or end. The current universe, with its billions of galaxies and trillions of stars, would merely be one chapter in an eternal cosmic rhythm: expansion, cooling, contraction, collision, rebirth. In this light, our universe is not a fleeting accident, but part of an ancient, ongoing process, one that has repeated perhaps countless times. The remnants of past cycles may still linger in the cosmic background, faint echoes from universes that came before our own. Though brain cosmology remains a speculative framework, it invites us to imagine existence on a scale far beyond the limits of our senses. It challenges us to reconsider what reality means when the true fabric of the cosmos may stretch into dimensions we cannot yet perceive. And somewhere, beyond the veil of our visible universe, other brains may be moving even now, drifting silently through the higher dimensional bulk until perhaps one day they collide again, giving birth to another universe and another story of creation. However, instead of expanding indefinitely, it eventually begins to slow, its vast outward rush losing momentum, as if the universe itself were taking a long, deep breath before exhaling once more. The galaxies, once racing apart, start to drift closer, pulled inward by gravity's patient hand. Slowly, inexorably, everything begins to contract. Over unimaginable spans of time, billions upon billions of years, stars burn out, galaxies fade, and the universe grows darker, colder, quieter. Then, in an extraordinary reversal, all matter and energy begin to collapse back toward a single, unimaginably dense point. Scientists call this hypothetical event the Big Crunch, a cosmic implosion where space, time, and energy fold back into themselves, returning the universe to a state as dense and hot as the one from which it was born. And from that state, some theorists argue, a new beginning could emerge, a new expansion, a new universe. This is the essence of the cyclic universe, a cosmos that does not begin once and end forever, but instead moves through infinite cycles of birth, growth, decay, and rebirth. According to this model, the universe breathes. Each cycle might last trillions of years. After each collapse, a new expansion begins, perhaps under slightly different conditions. Some versions of the theory suggest that with every new cycle, the physical laws themselves, those fundamental constants that define the structure of atoms, the speed of light, the strength of gravity, may shift ever so slightly. These subtle variations could explain why our particular universe appears so finely tuned for life. Perhaps countless cycles have unfolded before, and each one testing different versions of reality until one, like ours, gave rise to stars, planets, and the fragile emergence of consciousness. But the cyclic model faces profound challenges. Physicists have long questioned how such a universe could rebound from a complete collapse without breaking the laws of thermodynamics. The second law states that entropy, the measure of disorder, should increase over time. If each cycle accumulates more entropy than the last, how could the universe ever return to a low entropy state suitable for another Big Bang? For the cyclic model to work, something extraordinary must happen during the transition between contraction and expansion, something that resets the cosmic clock. Adding to the mystery, modern astronomical observations show that our universe's expansion is not slowing down, it is accelerating. Distant galaxies are racing away faster and faster, driven by what scientists call dark energy, an unknown force that seems to permeate all of space. This accelerating expansion makes a future contraction, the Big Crunch, seem unlikely. Instead, some cosmologists predict an ultimate Big Freeze, in which the universe continues expanding forever, growing colder and emptier until even atoms decay and time loses meaning. Others imagine a big rip where the expansion becomes so violent that galaxies, stars, and even subatomic particles are torn apart. In this view, there would be no bounce, no rebirth, just dissolution. Yet the idea of a cyclical cosmos refuses to fade. There's an undeniable poetic symmetry to it, a universe that continually renews itself, erasing its past while preserving its essence. The Big Bounce theory, for example, offers a more modern twist on the old cyclic idea. It suggests that when the universe reaches a critical point of density, quantum effects prevent it from collapsing into a singularity. Instead, the compression halts, reverses, and the universe bounces outward again. Space-time itself might be elastic, able to compress and rebound rather than break. This elegant solution sidesteps the problem of an infinite singularity and avoids the question of what came before the Big Bang, because there was always a before. Imagine it, an eternal cosmic heartbeat. Each universe expanding, maturing, collapsing, and then exploding into life once more. Time in this view is not a straight arrow, but a wheel, turning endlessly with no true beginning or end. The stars we see in our night sky might be just one moment in an infinite succession of cosmic ages, each separated by cataclysmic renewal. Still, the evidence remains elusive. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, align more closely with the predictions of inflationary models, which describe a single rapid expansion rather than repeated cycles. And while certain branches of string theory have proposed mechanisms, such as the collision of higher dimensional brains, that could trigger new universes, these ideas remain speculative. No telescope has yet glimpsed the scars of a previous cosmos written across the fabric of our own. But perhaps the question is not whether the cyclic model is true, but what it represents. Our search for meaning in an indifferent universe. We look for patterns because we hope the cosmos mirrors our own experience of life and death, decay and renewal. The cyclic universe speaks to that deep human longing for continuity, for the idea that even after an ending, something begins again. So the debate continues. The Big Bang remains our best supported explanation for the universe's origin, yet the cyclic view lingers at the edges of cosmology, whispering a tantalizing possibility that our universe is not a single fleeting event, but part of an eternal story, a story without beginning or end, a rhythm that echoes through time itself. However, the concept of ever-increasing entropy and the arrow of time pose profound and persistent challenges to these grand cosmic models. Entropy, often described as a measure of disorder or randomness within a system, steadily rises as time progresses, a principle enshrined in the second law of thermodynamics. This fundamental law, one of the cornerstones of physics, dictates that isolated systems evolve toward greater disorder, making the direction of time unmistakably one way. But if time truly has a direction, if the universe marches inexorably toward higher entropy, then how could it ever loop back on itself? This question lies at the heart of the tension between thermodynamics and the idea of a cyclic universe. In a universe that endlessly expands and contracts, each cycle would, in theory, begin with more entropy than the last. Over countless repetitions, the cosmos would grow increasingly disordered, its initial smoothness and simplicity lost forever. To confront this problem, some physicists have proposed ingenious, even radical, mechanisms to reset the cosmic clock. Certain models imagine that during the universe's contraction phase, as it begins to collapse in on itself, the arrow of time could somehow reverse. In that reversed state, entropy would decrease, effectively unwinding the disorder accumulated over billions of years. Other theories envision that as the universe expands, space stretches so vastly that entropy becomes diluted, spread across immeasurable distances until its effects all but vanish. In this scenario, the universe, in its sheer immensity, wipes its slate clean. Still, other cosmologists suggest that during the transition between cycles, new regions of low entropy could spontaneously emerge, fresh, pristine patches of spacetime from which a new universe might be born. These possibilities, while creative and mathematically intriguing, remain speculative. The entropy problem continues to loom as a formidable obstacle for any theory that dares to describe a universe without a true beginning or end. Yet the very persistence of this debate reveals something extraordinary. Scientists are not merely trying to describe the universe as it is, but to understand the deeper logic that governs existence itself, why time flows as it does, and whether that flow could ever be reversed. Dark energy, the mysterious force that drives the accelerated expansion of the universe, plays a central role in many cyclic cosmologies. In these models, the universe does not expand into an eternal void, but moves rhythmically through epochs of growth and collapse. As dark energy propels galaxies apart at an ever-increasing rate, matter becomes more and more diffuse. Stars die out, galaxies drift beyond each other's reach, and the universe fades toward a state of cold emptiness. Yet some cyclic theories propose that this very expansion carries the seeds of its own reversal. As the cosmic fabric stretches thinner and thinner, it might eventually reach a breaking point, a so-called Big Rip, where the structure of spacetime itself begins to tear. In that instant, the outward expansion halts, giving way to a mighty contraction. Gravity, once overpowered by dark energy, reasserts its dominance. The universe folds inward, collapsing back into a dense, fiery state, not unlike the one that existed before the Big Bang. This collapse, in turn, could ignite the next cosmic rebirth. Another Big Bang, another expansion, another age of stars and galaxies. Thus, the universe may be engaged in an endless dance of death and renewal, with dark energy and gravity as its eternal partners. Yet, the precise choreography of this cosmic rhythm remains unknown. How exactly does the universe switch from expansion to contraction? What physical laws govern the boundary between one universe and the next? These questions continue to captivate cosmologists who strive to decode the hidden patterns that shape our reality. If cyclic universe models prove correct, they would overturn our most basic assumptions about existence. Rather than a cosmos with a singular beginning, a unique moment of creation, reality itself might be cyclical, without origin or conclusion. Our current epoch would then be just one act in an infinite cosmic play, a brief scene in a story that repeats endlessly. This vision of the universe transforms our understanding of time, suggesting that the notion of a beginning may be an illusion born from our limited perspective. Within such a framework, causality, the chain of cause and effect that defines our experience of time, becomes less absolute. If every universe begets another, if entropy resets and creation repeats, then perhaps the very idea of time as linear is only a convenient fiction. Some versions of these models go even further, proposing that traces of previous cycles might survive within our own universe. Subtle imprints, patterns in the cosmic microwave background, or anomalies in the distribution of galaxies could be the echoes of earlier worlds. If discovered, such evidence would offer a tantalizing glimpse into the cosmic memory of the universe, suggesting that information or even the laws of physics themselves might persist across cycles. Each rebirth would then not be a complete erasure, but a transformation, a passing of the torch from one cosmos to the next. And yet, beyond these vast cosmological loops lies another idea, one that challenges our imagination even further. The white hole. A white hole is the theoretical mirror image of a black hole, a cosmic object not of consumption but of expulsion. While black holes are regions where gravity is so overwhelming that nothing, not even light, can escape, white holes would be the reverse, places where nothing can enter and from which matter and energy are endlessly ejected. The mathematics of Einstein's general relativity permits such entities, though they have never been observed. A white hole would blaze brilliantly against the darkness of space, an impossible fountain of light and matter pouring outward, forever unreachable from the outside. Some physicists speculate that a white hole might be the far end of a black hole, the exit of a cosmic tunnel known as a wormhole. In this view, whatever falls into a black hole could eventually reemerge elsewhere in the universe, or even in another universe entirely through a white hole. The two would form a bridge across space-time, a gateway between realms. Yet this concept poses staggering paradoxes. White holes would appear to defy thermodynamics, seemingly reversing the natural increase of entropy. They would also invert the arrow of time, turning collapse into expansion, consumption into creation. Whether such phenomena could ever exist beyond the mathematics that describe them remains uncertain. Despite their speculative nature, white holes continue to intrigue scientists because they represent one of the ultimate frontiers of theoretical physics. Together with black holes, they define the extremes of the cosmic spectrum, one absorbing, the other expelling. One cloaked in darkness, the other radiant beyond comprehension. Black holes are now well-documented features of the universe, their presence confirmed by gravitational waves, X-ray emissions, and even direct imaging. They're the endpoints of massive stars, the gravitational anchors of galaxies, and the silent engines of cosmic evolution. White holes, in contrast, remain phantoms of theory, possible perhaps, but unseen. Yet the very idea of them invites wonder. If black holes are the universe's way of concealing information, might white holes be its way of revealing it again? Could the two be parts of a single process, destruction and creation eternally intertwined? If so, then perhaps the story of the cosmos is not one of an ending or a beginning, but of perpetual transformation. Entropy, dark energy, black holes, and white holes all may be threads in the same vast tapestry, woven by the mysterious hand of time itself. However, unlike black holes, those cosmic monsters whose presence we've confirmed through the way they twist the motion of nearby stars and distort the glow of hot gas, white holes remain purely ghosts of mathematics. No telescope has ever glimpsed one. No signal has hinted at their existence. They live entirely within the equations of general relativity, whispering from the edges of theoretical physics. For decades, they have lingered as an idea, the mirror image of a black hole, something that might exist if the universe allows time itself to run in reverse. And yet, the idea refuses to die. To imagine a white hole is to turn the logic of gravity upside down. If a black hole is a cosmic sink, swallowing everything that comes near it, then a white hole would be a fountain of matter and light, forever outpouring and never taking in. It would be the ultimate source, a celestial geyser erupting from the void. Nothing could cross its boundary from the outside. It would repel the universe around it. For physicists, that makes it a deeply unsettling concept, but also an irresistible one. Some theorists go even further, proposing that white holes could be the birthplaces of entirely new universes. In this view, each black hole might not simply be an endpoint, but a doorway. The unimaginable compression within its core could, under certain conditions, trigger a kind of rebound, an explosion on the far side of space-time. That eruption could expand into its own cosmos, governed by its own physical laws, its own constants, its own stars and galaxies. Our universe, in this speculative picture, might itself have been born from the death of another, an offspring universe expelled through a white hole in some parent cosmos long gone. In the grandest interpretation, this process would not be rare, it would be endless, a self-replicating tree of realities branching through eternity. Still, the mathematics that describe such wonders are treacherous. On paper, white holes emerge naturally as solutions to Einstein's equations, just as black holes do. But in practice, the conditions required for their formation seem almost impossible. Any disturbance, even the smallest nudge, would destabilize them, causing them to collapse before they could exist long enough to be noticed. For this reason, many physicists view white holes as elegant but unrealistic, beautiful artifacts of theory rather than genuine features of the cosmos. Yet, beauty itself has often been a clue in physics, a hint that something deeper may be hiding within the equations. The idea that black holes could give rise to new universes is tied to a profound question: how does our universe renew itself? When a massive star collapses into a black hole, its core becomes so dense that known physics breaks down. Space and time themselves seem to crumple into a singularity, a point of infinite density where our equations fail. Some researchers suspect that at such extremes, quantum effects might ignite a kind of cosmic rebound, transforming collapse into creation. A singularity that implodes in one universe might explode as a big bang in another. In that sense, the death throes of one world could seed the birth of the next. This notion even offers a poetic symmetry to the cosmos. The black hole, symbol of destruction, would also be the midwife of creation. Our own universe, with its galaxies, stars, and life, could be the product of such a process, an echo from a deeper, older reality. If so, the cycle might never end, each universe spawning the next through the dark heart of its black holes, a perpetual cosmic heartbeat stretching across infinite generations. The fascination deepens when we consider the information paradox, a riddle that has haunted physicists for decades. According to quantum mechanics, information can never truly be lost. Yet when matter falls into a black hole, it appears to vanish completely, erased beyond the event horizon. This contradiction strikes at the very foundation of physics. But what if black holes and white holes are two halves of the same process? What if everything consumed by a black hole eventually reemerges from a white hole, elsewhere in space, or perhaps in another universe altogether? This idea conjures the image of a cosmic bridge, a wormhole or Einstein-Rosen bridge linking two distant realms. Through it, information would not be destroyed, but transferred, hidden from us yet preserved within the deeper structure of space-time. It's an intoxicating idea, a hidden network of cosmic tunnels, each black hole leading not to oblivion, but to birth. A white hole, on the far side, would erupt in a blaze of light and energy, releasing what was once consumed. In this vision, the universe becomes a living organism, its matter cycling endlessly through collapse and creation, death and renewal. But how would we ever know? Detecting a white hole, if such a thing exists, would be almost impossibly difficult. Unlike black holes, which betray themselves by the way they pull on their surroundings, a white hole would repel everything. Yet astronomers have speculated on possible clues. A sudden burst of energy appearing from nowhere, an explosion without a source, could be one. Gamma ray bursts, those mysterious flashes of high-energy light that flare and fade in moments, have been considered possible candidates. So too have ultra-high-energy cosmic rays, particles so powerful that their origins remain unexplained. A white hole, unleashing stored energy from some hidden domain, could provide the kind of violence needed to produce them. Gravitational waves might offer another window. If a white hole formed and collapsed almost instantly, it could send a unique ripple through space-time, a signature unlike anything produced by colliding stars or merging black holes. Detectors like LIGO and Virgo, attuned to the faint tremors of the universe, could in theory capture such signals. But so far, no such pattern has been found. The silence continues. Even so, the allure of white holes persists. They embody our most daring impulses in physics, the urge to look beyond the visible, to chase beauty through mathematics, to imagine that the cosmos might be far more intricate than it appears. Whether they exist or not, white holes push us to confront the limits of what we know. They ask whether creation itself might be cyclical, whether the end of one universe could be the beginning of another, and whether the laws that govern our reality might only be one chapter in a far larger story. As long as these questions remain unanswered, the idea of the white hole will continue to shimmer at the edge of science, part theory, part myth, part mirror reflecting our own desire to understand where everything begins and where it might someday end. However, it is important to note that even though mathematics allows for elegant solutions such as white holes and traversable wormholes, the cosmos itself has offered us no proof that either truly exists. Not a single telescope, detector, or gravitational signal has revealed their presence. Yet their equations emerge naturally from the very fabric of Einstein's general relativity, hinting that the universe may still be hiding such wonders just beyond the reach of our instruments. The connection between white holes and wormholes reveals an intricate web woven into the geometry of space-time itself. Both concepts stretch our understanding of cause and effect, forcing physicists to question what it really means for one event to lead to another. In the equations of relativity, time and space are not rigid frameworks, but pliable entities that twist and fold under gravity's immense pull. Within these folds, theoretical gateways might exist, tunnels linking not only distant regions of space, but possibly even different universes altogether. And yet, these ideas remain shrouded in speculation. White holes, if they exist, are the mirror image of black holes. Where black holes consume matter, white holes would violently expel it, releasing energy and particles into the surrounding cosmos. Nothing could enter a white hole. Its very nature would forbid it. Some physicists have taken this symmetry further, proposing that perhaps the Big Bang, the violent moment that gave birth to our universe, was not a beginning at all, but rather an explosion from a white hole existing in another universe. In this scenario, our cosmos would be the outflow of matter and energy ejected from a dying region of a different space-time. The idea is both haunting and beautiful. Imagine a cosmic chain where every universe is born from the ashes of another, connected through the mysterious corridors of wormholes. In one universe, a black hole collapses. In another, a white hole erupts, each an echo of the other, bound across the boundaries of existence. Theoretical models even allow for these bridges, suggesting that a black hole's interior might connect to a white hole's mouth somewhere else, though the physics required to keep such a passage open defies our current understanding. Despite the allure of these possibilities, the reality remains cold and silent. No observation confirms white holes. No evidence indicates that wormholes can exist in a stable form. The equations are there, but the universe has yet to whisper a hint that they manifest in nature. For now, they live in the realm of mathematics and imagination, where the limits of general relativity meet the mysteries of quantum mechanics. The search for a deeper theory, one uniting gravity with the strange rules of the quantum world, has led scientists to another revolutionary concept, the holographic principle. This idea suggests that everything we experience as three-dimensional might, in truth, be information projected from a two-dimensional surface. Picture a hologram. A flat image etched on glass can produce the illusion of depth when illuminated by light. Now, stretch that analogy to the entire cosmos. Our vast three-dimensional universe could be a projection, its every atom and galaxy encoded on a distant cosmic boundary. This concept first arose from the study of black holes. Physicists discovered that the amount of information or entropy a black hole can contain is proportional not to its volume, but to the area of its event horizon. That finding was stunning. It suggested that reality's information might always reside on surfaces, not within volumes. From this insight came the idea that perhaps the universe itself operates like a grand hologram, where every particle, every field, and even gravity is a projection of deeper information imprinted on a cosmic boundary. In this framework, what we perceive as three-dimensional motion and depth might be an illusion, a shadow cast by fundamental processes occurring on a two-dimensional stage. The implications are profound. It challenges our sense of what real means. If the holographic principle holds true, then our experience of existence could be a sophisticated projection, where space, time, and matter are emergent properties rather than fundamental building blocks. String theory provides crucial support for this breathtaking idea. According to string theory, the universe's smallest components are not point-like particles, but minuscule vibrating strings. Their vibrations determine the nature of all matter and forces, and their behavior unfolds in dimensions beyond those we can perceive. In certain versions of string theory, researchers found that a theory describing gravity in a curved space can be exactly equivalent to a quantum theory without gravity on a flat lower dimensional surface. This relationship is known as the anti-de Sitter conformal field theory correspondence, or more simply, the ADS-CFT correspondence. This discovery was nothing short of revolutionary. It provided a mathematical realization of the holographic principle, showing that the physics within a volume of space could indeed be encoded entirely on its boundary. In practical terms, it means that to understand gravity, scientists can study equivalent systems that do not even include gravity at all, a stunning reversal of how we traditionally think about the universe. Experiments, too, have begun to echo these ideas. Quantum simulations have shown that holographic models can accurately describe certain quantum systems, suggesting that this principle may not be confined to theory alone. These laboratory-scale glimpses into holography hint that our universe could indeed operate on similar principles, where the deepest truths of space and time might be written on a cosmic screen beyond our perception. If the holographic universe theory is correct, it could be the missing key to unite quantum mechanics and general relativity, the two great pillars of modern physics that, for over a century, have resisted reconciliation. It would mean that gravity itself might be a manifestation of quantum information projected from a boundary beyond our reach. And so scientists continue to probe the edges of reality, exploring black holes, simulating quantum systems, and questioning the very fabric of space and time. Whether the universe is born from a white hole, connected through wormholes, or projected from a two-dimensional horizon, each discovery brings us closer to understanding that our cosmos might not be as it appears. It could be a grand illusion, a cosmic hologram written in light and mathematics, waiting for us to finally read its code. Conversely, it opens a fascinating window into the workings of quantum systems by creating an unexpected bridge to gravitational theories. This remarkable connection between string theory and the holographic principle has captivated physicists for decades, evolving into a dynamic field of research that promises to illuminate the deepest mysteries of the universe. By linking the behavior of subatomic particles to the vast architecture of space-time, this intersection offers the tantalizing possibility of uncovering a unified understanding of reality itself, merging the infinitely small with the infinitely large in ways previously thought impossible. The concept of a holographic universe is not just an abstract notion confined to theoretical equations. It fundamentally challenges our perception of space, dimensions, and reality. Imagine that the three-dimensional world we navigate daily, with its length, width, and depth, is not the ultimate stage of existence, but rather a projection, akin to a hologram emerging from a distant two-dimensional surface. This idea arises from the holographic principle within string theory, a principle suggesting that the information necessary to describe a volume of space may in fact be encoded entirely on its bounding surface. If true, this revelation forces a radical reevaluation of concepts as elemental as up, down, left, and right, implying that what we perceive as spatial directions may be emergent illusions generated by deeper informational structures. Moreover, the holographic perspective suggests that our experience of depth and dimensionality might be a secondary phenomenon rather than a fundamental trait of reality. It could explain why quantum mechanics, which often manifests in lower dimensional behaviors, can appear so disconnected from the three-dimensional classical world we inhabit. By providing a framework in which these quantum behaviors are naturally projected into three dimensions, the holographic principle may offer new insights into the enigmatic phenomena of quantum entanglement and the paradoxical properties of black holes, potentially reconciling long-standing conflicts between quantum theory and general relativity. A particularly striking implication of the holographic universe model concerns the limits of information storage. If all the data within a volume of space can be encoded on its surrounding surface, then the universe itself imposes a fundamental cap on the amount of information that can exist in any given region. This notion reshapes our understanding of physics, computation, and even consciousness, suggesting that reality may be governed not solely by material interactions, but by the flow and structure of information across space-time. In practical terms, this perspective also challenges how we conceive of the boundaries of the cosmos. If our universe operates holographically, then the edge of everything we observe may act as a cosmic horizon, a repository of information capable of describing the entirety of the universe it encloses. The third dimension, then, becomes a perceptual effect, emerging from the way information is projected from this boundary. Questions about what lies beyond the universe take on entirely new meaning. Beyond may no longer signify an unreachable expanse of space, but rather the structure and organization of information on distant two-dimensional surfaces, potentially hinting at other universes encoded in the same manner. The holographic principle also strengthens the profound ties between string theory and quantum gravity. It implies that the fundamental rules governing the smallest scales of reality may be inseparably linked to the structure of the cosmos on the grandest scales. Understanding the universe, therefore, requires exploring the interplay between the tiniest quantum fluctuations and the cosmic architecture that stretches across billions of light years. Experimental physicists have embarked on daring efforts to probe these ideas. One such endeavor is the holometer experiment at Fermilab, which employs highly precise lasers to detect minute jitters in spacetime that could hint at its granular, holographically encoded structure. By measuring fluctuations at scales far smaller than atoms, scientists hope to uncover evidence that our three-dimensional reality emerges from information stored on a two-dimensional plane. Another approach involves the cosmic microwave background, the faint afterglow of the Big Bang. Researchers scrutinize its subtle patterns for signs of holographic noise, tiny deviations that might suggest the early universe encoded information holographically. Black holes, with their extreme gravitational fields, also serve as critical testing grounds. Studying how information behaves near event horizons may reveal how the universe maps three-dimensional phenomena onto two-dimensional boundaries. Quantum entanglement experiments further probe the distribution of information across space, offering additional insight into whether reality itself may be fundamentally informational rather than material. Through these experiments, the boundaries of knowledge are being continually pushed. From high-precision laboratory setups to large-scale astronomical observations, scientists are exploring whether our universe functions as a vast hologram, where all the richness of experience, matter, energy, motion, and even consciousness emerges from the organization of information on a lower dimensional surface. At the heart of this theory is a vision of reality that is both profound and counterintuitive. Everything from the chair beneath our hands to the farthest galaxy could be a projection from a cosmic two-dimensional boundary, with the holographic encoding defining what we perceive as physical existence. This reconceptualization has far-reaching consequences for black holes, quantum mechanics, and consciousness itself. The solidity of matter, the passage of time, and the very fabric of space may all be emergent features of a deeper, information-based reality. If the holographic principle holds, our place in the cosmos shifts dramatically. We are not merely observers of a three-dimensional universe, but participants in an intricate projection of encoded information, navigating a reality far stranger and more intricate than our senses reveal. Central to these ideas are quantum fluctuations, the fleeting and ceaseless changes in energy that pervade the universe at the smallest scales. Governed by the uncertainty principle, which forbids the precise simultaneous measurement of certain pairs of properties such as position and momentum, quantum mechanics reveals that even empty space seethes with activity. Particles appear and vanish, borrowing energy from the vacuum in incredibly brief instants. These ephemeral events, imperceptible to the naked eye, yet fundamental to the workings of nature, provide the fluctuating canvas upon which the universe paints its complex structure. The interplay of these fluctuations with the holographic encoding of reality suggests that even the tiniest disturbances at the quantum level may be inextricably linked to the vast cosmic structure, hinting at a unity between information, space, and time that we are only beginning to grasp. In sum, the holographic universe represents not just a radical scientific hypothesis, but a profound reimagining of reality itself. It bridges the microscopic and macroscopic, the quantum and the cosmic, offering a vision of a universe in which the familiar dimensions of our everyday experience may be mere projections of a deeper, information-rich substratum. The quest to understand this hidden structure continues to drive cutting-edge experiments and theoretical breakthroughs, promising a future in which humanity may finally glimpse the true architecture of the cosmos. However, the invisible ripples of the quantum world leave their mark in ways both subtle and extraordinary, revealing a universe that is far stranger than our everyday experiences would suggest. Quantum fluctuations, tiny, seemingly random jitters in energy, play a pivotal role in the cosmos. They were the silent architects of the early universe, seeding minuscule irregularities that, over billions of years, expanded and coalesced into the vast cosmic web we witness today. Sprawling galaxies, clusters, and immense filaments stretching across unimaginable distances. These fluctuations do not merely belong to the past. They persist, quietly shaping the behavior of particles and fields at the quantum level, often defying classical logic and intuition. At the very smallest scales of reality, the quantum realm dances to rules that challenge common sense. In this bizarre microcosm, particles blink into existence from the vacuum itself, only to vanish moments later, leaving behind a ghostly trace of their presence. Most of the time, these ephemeral fluctuations average out, leaving no lasting imprint. Yet under certain extraordinary conditions, their impact can be cosmic. Theories suggest that a sufficiently intense fluctuation could spark a rapid, localized expansion of space, a process known as quantum nucleation. From such an event, a new bubble of space-time could emerge, a nascent universe gestating within the quantum foam, waiting to unfold. Cosmic inflation theory provides a compelling framework for understanding how these tiny quantum ripples could be amplified into the vast structures we observe today. In the universe's first fractions of a second, space itself expanded exponentially, stretching the minutest quantum variations to scales that spanned light years. These magnified irregularities ultimately became the seeds from which galaxies and galaxy clusters grew, shaping the universe's grand architecture. This perspective opens doors to the notion of a multiverse, an endless collection of universes, each born from its own quantum fluctuation, each with potentially different physical laws and histories, nestled within an eternal sea of quantum possibilities. Underlying this dynamic cosmic tapestry is the concept of quantum foam, a term describing space-time at its most fundamental and turbulent levels. Far smaller than atoms, space-time at this scale is anything but smooth. It churns and froths, brimming with energy, reminiscent of waves breaking on a stormy ocean. Within this frothy landscape, virtual particles and their antiparticles continuously wink into and out of existence, creating a restless, ever-changing fabric of reality. Some physicists speculate that our entire universe could have emerged from a particularly large fluctuation in this quantum foam, a scenario that resonates with models of cosmic inflation, where a tiny point of space-time ballooned to cosmic proportions in the universe's earliest moments. The quantum world's unpredictability is intimately tied to the uncertainty principle formulated by Werner Heisenberg. According to this principle, certain properties of particles, such as position and momentum, cannot be measured simultaneously with absolute precision. This built-in fuzziness allows energy itself to fluctuate briefly, violating conservation laws for infinitesimal moments. Such fluctuations generate the restless, bubbling quantum foam, where particles and antiparticles continuously appear and annihilate each other, and where the fabric of reality itself seems alive with activity. These effects are not mere abstractions. They manifest in observable phenomena, like the Casimir effect, where two uncharged metal plates in a vacuum experience a tiny attractive force due to differences in quantum fluctuations between the plates and the surrounding space. The implications of quantum fluctuations extend far beyond abstract theory. They offer insight into the early universe's evolution, potentially explain the birth of cosmic structures, and even hint at technological possibilities rooted in harnessing quantum effects. The very idea that the cosmos could arise from a quantum fluctuation, something appearing from seemingly nothing, challenges our deepest intuitions about existence. It stretches the boundaries of scientific understanding, inviting speculation about realities far richer and more complex than those we can directly observe. Some cosmologists propose that a massive fluctuation in the quantum vacuum could have provided the spark for cosmic inflation, setting in motion the rapid expansion that ultimately led to the Big Bang. This theory harmonizes with quantum mechanics, offering a tantalizing explanation for how an entire universe could emerge from a state that, to classical eyes, seems empty. Yet, these ideas remain profoundly speculative. The universe's first instance lie on the reach of direct observation, leaving scientists to rely on theory, indirect evidence, and the careful interpretation of cosmic imprints. Another perspective, the zero-energy universe hypothesis, suggests that the total energy of the cosmos might be precisely zero, with the positive energy of matter exactly balanced by the negative energy associated with gravity. In such a scenario, the universe could arise from nothing, without the need for an external energy source. This radical concept forces a reevaluation of what creation truly means, demonstrating that even seemingly empty space is pregnant with potential, and that the cosmos itself may be the most extraordinary manifestation of the quantum rules that govern reality at the smallest scales. Through these intertwined ideas, quantum fluctuations, quantum foam, the uncertainty principle, and cosmic inflation, we begin to glimpse a universe that is both delicate and resilient, spontaneous and structured. A universe where the tiniest flickers of energy can ripple outward to shape galaxies, where the fabric of space-time itself is alive with restless activity, and where the boundaries of the possible extend far beyond imagination. In studying these phenomena, we confront not only the origins of our cosmos, but also the astonishing, unbounded creativity of the quantum world, a world that continues to challenge, inspire, and redefine our understanding of reality itself. However, the zero-energy hypothesis offers a strikingly elegant perspective on the fundamental balance of our universe. It proposes that all the visible energy we observe, everything from the blazing light of stars to the motion of galaxies, is precisely counterbalanced by an equal quantity of negative gravitational energy. Unlike the forces that push or pull at close range, gravity is a relentless, ever-attractive force operating across incomprehensibly vast cosmic distances. As the universe continues its expansion, it must continually expend energy to overcome this gravitational pull. According to the zero-energy hypothesis, the energy required to drive this expansion is exactly equal in magnitude, but opposite in sign to the positive energy of matter, achieving a perfect cosmic equilibrium. If this remarkable balance truly exists, it reshapes our understanding of the cosmos, offering a framework in which the universe could have spontaneously arisen without infringing upon the most sacred principle in physics, the conservation of energy. For decades, cosmologists and theoretical physicists have been captivated by this concept, probing its implications and testing its limits. It touches on one of the deepest questions imaginable. How can a universe of such staggering complexity and diversity emerge seemingly from nothing? Here, quantum mechanics provides a crucial window. At scales far smaller than atoms, the vacuum of space is never still. What appears to be empty is instead a seething, restless medium filled with ephemeral activity. Particles and antiparticles constantly materialize from the quantum vacuum, only to vanish moments later in an intricate dance of creation and annihilation. These fleeting entities, termed virtual particles, exist for such unimaginably short intervals that their presence is almost ghostly. Yet they are a direct consequence of the uncertainty principle, which allows temporary, minute violations of energy conservation. The cumulative effect of these quantum fluctuations is an underlying energy that suffuses all of space, a hidden engine driving subtle phenomena in the cosmos. The relevance of quantum fluctuations becomes especially profound when considering the origins of the universe itself. Some theoretical models suggest that a fluctuation of sufficient magnitude within the quantum vacuum could have triggered the explosive expansion known as cosmic inflation, essentially giving birth to the entirety of our observable universe. In this scenario, everything we see, from the grand spiral arms of galaxies to the tiniest speck of interstellar dust, emerged from what can only be described as a quantum hiccup in the fabric of space-time. While it seems counterintuitive, even paradoxical, the emergence of something from an apparent nothingness is fully consistent with the bizarre and fascinating rules of quantum mechanics. Time and again, experiments at microscopic scales have revealed that our classical intuition cannot grasp the true nature of reality, which is often far stranger than fiction. Virtual particles occupy a central role in this story of cosmic genesis. Though they exist only briefly before annihilating each other, their fleeting presence is far from trivial. In the earliest instance of the universe, these ephemeral particles may have acted as the sparks from which all matter and energy ignited. Some cosmologists propose that our cosmos began in a manner akin to the birth of virtual particles, a sudden transient fluctuation in the quantum vacuum that expanded rapidly to create space, time, and matter as we know them. In this view, the early universe was a frothing, energetic expanse where the ephemeral became eternal, where the transient interactions of quantum entities seeded the vast cosmic structures we observe today. During cosmic inflation, these quantum fluctuations were stretched across unimaginable distances, leaving imprints that would later evolve into galaxies, clusters, and immense cosmic voids. The patterns of these fluctuations, frozen into the fabric of spacetime, provide the scaffolding for the universe's large-scale structure. Without the ephemeral ballet of virtual particles during these formative moments, the cosmos might never have taken the shape we now observe, from the largest filaments of galaxy superclusters to the sparse, dark chasms that punctuate the cosmic web. In contemplating these phenomena, one begins to see the universe not as a static expanse, but as a dynamic, evolving tapestry, woven from the interplay of positive and negative energies, the dance of creation and annihilation, and the profound mysteries of the quantum world. Each flicker of a virtual particle, each subtle fluctuation in the vacuum, may hold the key to understanding the universe's origin, its astonishing growth, and the delicate balance that allows existence itself. The zero-energy hypothesis and quantum fluctuations together paint a picture of a cosmos that is simultaneously orderly and chaotic, predictable in its laws, yet endlessly surprising in its manifestations, inviting humanity to peer ever deeper into the profound enigma that is reality. Furthermore, virtual particles play an astonishing role in shaping our understanding of both black holes and the possible birth of entire universes. In the cold, mysterious depths of space, near the edge of a black hole's event horizon, pairs of these fleeting particles appear and vanish in an endless dance of creation and annihilation. Stephen Hawking's groundbreaking insight revealed that when one of these virtual particles escapes the gravitational pull while its partner falls into the black hole, radiation is released, a process now known as Hawking radiation. Over immense periods of time, this radiation could even cause black holes to evaporate, transforming our understanding of cosmic evolution itself. And yet some theories go even further. They suggest that inside a black hole, beyond the veil of what we can observe, entire new universes might be forming, newborn realities spun from the collapse of another. If true, then virtual particles are not just ephemeral messengers of quantum uncertainty. They could be the bridge between existences, linking one cosmos to the next. Each black hole, then, might serve as a cosmic womb, giving birth to new universes in an infinite chain of creation. From this profound mystery of physics emerges another, a philosophical idea that stretches both science and imagination to their limits, the simulation hypothesis. It proposes that everything we experience, our universe, our consciousness, every atom and star, could be part of an artificial simulation designed by an advanced intelligence. According to this theory, reality itself might be nothing more than an intricately programmed construct, like a cosmic computer rendering existence frame by frame. Supporters of the idea point to the rapid growth of human technology as a precursor. In a mere few decades, we have evolved from the pixelated simplicity of early video games to virtual environments that mimic reality with astonishing precision. Extrapolate that progress thousands or millions of years into the future, and it becomes conceivable that civilizations far beyond our own might possess the power to simulate entire universes, down to the behavior of every particle and the thoughts of every conscious being within them. If such simulations are possible, then, as philosopher Nick Bostrom famously argued, it becomes statistically more likely that we are already living in one rather than existing in a single base-level reality. The logic is dizzying but compelling. If advanced beings can create countless simulated realities, and each of those can in turn produce their own simulations, then we could easily be part of a nested structure, one universe within another, like cosmic Russian dolls extending infinitely inward. This perspective raises staggering questions about the nature of existence. What is consciousness, if it can emerge within a simulation? Are we truly self-aware, or are our thoughts the results of coded processes too complex for us to perceive? And if there are creators of our simulated universe, who created them? The parallels with physics are haunting. The quantized, discrete nature of reality, where energy levels and particles come in tiny indivisible packets, resembles the binary structure of digital information. Even the observer effect in quantum mechanics, where particles behave differently when measured, can be interpreted as evidence of rendering on demand, a concept eerily similar to how computer systems conserve resources by simulating only what is observed. Imagine for a moment that the universe itself is a vast, elegant program. Every physical law from gravity to electromagnetism would then be a line of code. Every star, galaxy, and atom a data structure in a cosmic algorithm. The Big Bang might have been the moment the simulation booted up, the ultimate initialization event. In this light, black holes could represent not only cosmic mysteries, but also computational boundaries, regions where information is compressed or transferred, perhaps into other simulated realms. The connection between black holes and virtual particles might, in a strange symmetry, mirror the architecture of the simulation itself, where information never truly vanishes but instead transforms, spawning new layers of reality. The implications are both thrilling and unsettling. If our universe is simulated, then there exists a creator or creators, entities with technological powers beyond comprehension. What would their intentions be? Are we part of an experiment, an art project, or a means for them to study their own origins? Perhaps they observe us with the same curiosity we reserve for our own artificial intelligence. Such a revelation would shake the foundations of philosophy, science, and spirituality. The meaning of life, the nature of morality, and the concept of free will would all demand re-examination. If our thoughts and choices are products of a simulation, do we possess true agency? Or are we performing within parameters, convinced of our freedom while existing inside constraints we can never escape? Despite its speculative nature, scientists and philosophers have proposed ways to test the simulation hypothesis. One approach involves searching for signs of digital granularity in space-time, a smallest possible unit of reality, much like a pixel or a frame rate in a video game. If such a fundamental quantum of space exists, it could indicate that the universe is, at its deepest level, discrete rather than continuous. Another line of research involves looking for computational shortcuts, patterns, anomalies, or irregularities in physical constants that might betray an underlying algorithmic structure. Some have even suggested that if our universe is simulated, there might be detectable glitches or optimization processes where computational power is conserved in regions not under direct observation. An elegant explanation for the strange behavior of quantum particles when unmeasured. Ultimately, the simulation hypothesis serves as both a scientific and existential mirror. Whether true or not, it forces us to confront the fragility of our assumptions about reality. If the cosmos is a vast computation, then our search for meaning, our art, our science, our love, may be part of the very code that sustains it. And perhaps, just perhaps, the act of questioning our reality is itself a clue, an echo in the system, suggesting that self-awareness is not a bug in the simulation, but its purpose. Ultimately, arriving at a definitive answer to the simulation hypothesis, whether our universe is indeed an elaborate digital construct or a fully real physical reality, remains one of the most profound and elusive challenges in contemporary science and philosophy. Attempting to confirm or disprove this idea pushes the limits of both human imagination and empirical investigation, because so much of the inquiry hinges on assumptions about the capabilities, intentions, and limitations of a hypothetical simulator. As observers embedded within such a system, we may never fully comprehend its rules, motives, or methods. Yet, even the pursuit of these questions profoundly stretches our understanding of computation, reality, and consciousness. A universe constructed as a simulation would inevitably face significant constraints. At the forefront of these would be computational power. Even with technologies far beyond our current capabilities, the task of modeling every particle, every interaction, and every nuance of an entire cosmos would demand astronomical processing capacity, likely orders of magnitude beyond anything we could conceive. To manage this, a simulated universe would almost certainly simplify by compress or abstract certain details, much as modern computer graphics render distant objects with fewer polygons. This could mean that at the most fundamental levels, the physics and constants we observe may differ subtly from those in a real universe, deviations that might only become apparent under extreme conditions or through precise experimentation. Beyond the mechanical constraints of computation, there are profound philosophical and technical hurdles in simulating consciousness. Creating entities that possess self-awareness, subjective experience, and free will is no trivial task. Even if a simulation could mimic outward behaviors, replicating the internal phenomenology, the very essence of what it feels like to be conscious, may lie beyond the reach of computation. If true consciousness cannot be replicated, simulated beings might exist in a liminal state, capable of interacting and responding convincingly, yet devoid of the inner experience we associate with awareness. Additionally, simulations would likely be bounded in both scale and scope. Their creators might choose to focus on certain regions or aspects of reality, leaving others less detailed or entirely abstracted. This selective focus could manifest as anomalies, inconsistencies, or gaps in the richness of the simulated world. Such constraints highlight a striking tension. A universe that feels infinite to its inhabitants may, in fact, be carefully optimized and constrained by unseen architects. The simulation hypothesis forces us to confront questions that go to the heart of existence. If our reality is digitally constructed, every particle, every star, every thought and emotion is ultimately information being processed by a vast computational framework. Our consciousness, typically regarded as the foundation of our being, could itself be a sophisticated algorithm running within this system, raising fundamental questions about free will, determinism, and the nature of identity. Are our choices truly our own, or merely outputs of a vast preordained program? Even the laws of physics may be nothing more than the coded parameters set by the creators, suggesting that the constants and forces we observe are not universal absolutes, but deliberate design choices. The implications extend beyond metaphysical speculation. If reality is computational, then fields such as physics, neuroscience, and artificial intelligence may require a radical rethinking. The strategies we employ to understand the universe, whether through experimentation, observation, or mathematical modeling, might be constrained not just by practical limitations, but by the architecture of the underlying simulation itself. As our own technology progresses, creating increasingly complex virtual worlds, the line between simulated and physical reality may blur, offering glimpses of the same questions that have haunted thinkers contemplating our universe for millennia. Amidst this contemplation of artificial universes, real mysteries of our cosmos continue to unfold. Dark energy, for instance, represents a force both enigmatic and essential, responsible for driving the accelerating expansion of the universe. First observed in the late 1990s through studies of distant supernovae, dark energy appears to constitute approximately 68% of the total energy content of the cosmos. Unlike gravity, which pulls matter together, dark energy acts as a repulsive force, pushing galaxies apart and accelerating the expansion of space itself. Its influence becomes especially dominant on cosmic scales, shaping the large-scale structure of the universe as clusters of galaxies drift increasingly farther apart, while local gravitational interactions remain relatively unaffected. Physicists have proposed various frameworks to explain dark energy. One compelling possibility is that it represents the energy inherent to empty space, the so-called vacuum energy, an idea with profound implications for quantum theory and cosmology. Another hypothesis envisions dark energy as a dynamic field whose intensity may vary over time and space, adding a temporal complexity to the structure of reality itself. Observational astronomy, coupled with theoretical physics and advanced computational models, remains at the forefront of unraveling this mystery, as understanding dark energy is essential for predicting the ultimate fate of the cosmos. Will the universe continue to expand indefinitely, grow cold and desolate, or evolve in ways yet unimagined? Dark energy also sparks speculative intersections with the simulation hypothesis and multiverse theories. Some theorists ponder whether this invisible force could represent interactions between our universe and others, perhaps acting as a bridge to realms beyond our perceptible cosmos. While these ideas remain speculative, they highlight how the study of dark energy and the exploration of simulated realities share a common thread. Both challenge our most basic assumptions about the nature of existence and the universe we inhabit. In the end, whether we are inhabitants of a computational simulation or explorers in a universe dominated by the mysterious influence of dark energy, the pursuit of understanding propels us forward. It is a journey that blends physics, philosophy, computation, and imagination, a quest to uncover the architecture of reality itself, the limits of consciousness, and the forces shaping the cosmos on scales both vast and infinitesimal. In probing these questions, humanity pushes the boundaries of knowledge, navigating the interface between the conceivable and the unknowable, between the tangible universe and the tantalizing possibility that reality itself may be something far stranger than we have ever imagined. However, it is essential to recognize that this notion remains deeply speculative, resting more on imagination than on hard evidence. Current scientific understanding provides no concrete mechanism by which dark energy could act as a tangible bridge between separate universes. The difficulty arises from the very nature of such hypothetical universes. If they do exist, they would likely remain entirely isolated from our own, inaccessible to observation, and impervious to any form of interaction. Despite this, the idea of dark energy serving as a cosmic connector is undeniably compelling, capturing the imagination of both scientists and the public alike. Research continues to focus on understanding dark energy's intrinsic properties within the confines of our observable cosmos, probing how this enigmatic force influences the universe we can see. With ongoing studies and increasingly sophisticated experiments, there's hope that the true nature of dark energy might eventually reveal surprising insights, perhaps even hinting at unseen structures beyond the limits of our cosmic horizon. Among the more dramatic theories surrounding the ultimate fate of the cosmos is the Big Rip, a scenario that envisions an accelerating expansion so extreme that it could eventually dismantle all matter in the universe. This catastrophic vision begins with the largest cosmic structures, galaxy clusters and galaxies themselves, being pulled apart, and then extends down to stars, planetary systems, and ultimately the atoms that constitute everything we know. The theory is intimately linked to our understanding of dark energy, the mysterious, pervasive force that drives the accelerating expansion of space. In the Big Rip scenario, dark energy would not remain constant. Instead, it would grow progressively stronger over time, eventually overwhelming the fundamental forces that bind matter together. The key to understanding this possibility lies in a property known as the equation of state, a numerical descriptor of dark energy's behavior. If this value were to fall below -1, it would indicate that the density of dark energy increases as the universe expands, creating a runaway effect. Such a feedback loop would accelerate cosmic expansion to unimaginable rates, ultimately tearing apart the very fabric of space-time. Although this vision is striking in its dramatic implications, it remains a theoretical construct. Observations thus far suggest that dark energy's equation of state hovers close to, but not below, -1. Still, with future observations and more precise measurements, scientists may refine their predictions and clarify whether a Big Rip could ever become reality. Dark energy's influence is central to the long-term evolution of the universe. This enigmatic force, which constitutes roughly 68% of the cosmos's total energy, acts in opposition to gravity, exerting a repulsive pressure that accelerates the universe's expansion. As time progresses, its influence grows ever more dominant, reshaping the cosmic landscape in ways that challenge intuition. Should dark energy maintain its current characteristics, the universe is expected to drift toward a big freeze, a state in which galaxies recede from one another faster than the speed of light, eventually becoming isolated islands in an increasingly empty cosmos. Over unimaginably vast stretches of time, even stars and planets would become lonely travelers in a cold, dark, and ever-expanding void. Alternatively, if dark energy grows in intensity, it could precipitate the Big Rip scenario, where its repulsive power becomes so extreme that it overwhelms all forces holding matter together, leading to a violent tearing of galaxies, solar systems, planets, and even the atomic constituents of matter itself. Conversely, if dark energy were to weaken or change character over cosmic timescales, it could slow the expansion or even reverse it, potentially culminating in a Big Crunch, a cosmic implosion where the universe collapses back onto itself. In essence, the ultimate destiny of the universe is inseparably tied to the mysterious properties of dark energy, making it one of the most critical subjects in modern cosmology. Theories attempting to explain dark energy abound, each seeking to unravel the enigmatic force behind the accelerating expansion of space. One widely discussed possibility is that dark energy is an inherent property of space itself, a cosmological constant, as first proposed by Albert Einstein. This form of energy would be uniform and unchanging, an intrinsic feature of the vacuum that exerts a repulsive influence on the cosmos. Other scientists speculate that dark energy could take the form of a dynamic, evolving field, sometimes referred to as quintessence, which changes over time and across space. This model envisions a fluid-like energy permeating the universe, reminiscent of ancient philosophical ideas of a fifth element, an all-encompassing substance that binds the cosmos together. More radical hypotheses even challenge our understanding of gravity. Some researchers propose that the apparent effects of dark energy might be explained not by an unknown force, but by a modification of gravity itself. These theories suggest that the behavior of gravity on cosmological scales could differ from what we observe locally, implying that our current physical laws might be incomplete when applied to the universe at large. Each of these approaches highlights the profound challenge that dark energy poses. It forces scientists to reconsider foundational principles of physics, suggesting that our understanding of the cosmos is far from complete. The discovery of dark energy in the late 1990s, through careful observation of distant supernovae, fundamentally changed our view of the universe. Contrary to expectations, the universe's expansion was not slowing down under gravity's pull, but accelerating. This unseen force, now termed dark energy, is thought to comprise about 68% of the universe's total energy content, yet it remains undetectable directly. Its presence challenges established laws of physics, implying that our understanding of gravity and quantum mechanics may be incomplete, and raising profound questions about the universe's ultimate fate. Some theorists speculate that dark energy could hint at realities beyond our observable cosmos. Ideas derived from string theory and the multiverse hypothesis suggest that our universe might be only one of countless others, each possibly interacting in ways that manifest to us as dark energy. In such a framework, what we observe might be the influence of hidden dimensions or parallel universes subtly affecting the expansion of our own cosmos. While these ideas remain speculative, they underscore the tantalizing possibility that dark energy may not merely shape our universe, it might also serve as a window into a far broader cosmic landscape, stretching beyond the limits of what we can currently see or measure. In every sense, dark energy represents one of the most profound mysteries in modern science. It challenges our understanding of the universe on the largest scales, reshaping our view of cosmology and inspiring a host of theoretical explorations. Whether it ultimately leads to the slow dispersal of galaxies, a catastrophic cosmic tear, or the unveiling of hidden universes, the study of dark energy continues to push the boundaries of human knowledge, inviting us to ponder the unimaginable vastness and complexity of the cosmos. However, it is essential to emphasize that all of these ideas, while tantalizing and intellectually stimulating, remain largely speculative. To date, they lack the kind of concrete, direct observational evidence that would allow scientists to assert them with certainty. The quest to understand dark energy, a mysterious force that appears to drive the accelerated expansion of the universe, remains one of the most profound challenges in modern cosmology. Researchers across the globe are actively investigating a wide array of possible explanations. Some focus on subtle modifications to Einstein's century-old theory of general relativity, considering whether our understanding of gravity itself might need refinement on cosmic scales. Others hypothesize entirely new fundamental particles or fields lurking within the fabric of our universe, invisible yet influential, quietly shaping the expansion of space. As our instruments grow more precise and our surveys of the cosmos extend ever deeper, the hope is that these theories will be tested and refined, ultimately revealing the true nature of dark energy, whether it emerges from realms beyond our observable universe or from yet undiscovered properties inherent to it. The very pursuit of this knowledge pushes the boundaries of human understanding, demanding both creativity and rigor as we confront one of the universe's most profound enigmas. Cosmic topology, a field that might sound abstract or purely mathematical at first, is in fact a vibrant and deeply consequential area of study in cosmology. It investigates the large-scale shape and structure of the universe itself. Questions abound. Is space infinite or finite? Does it curve upon itself, looping back in ways that defy our everyday experience? Could it possess hidden connections, forming patterns or structures invisible to our immediate perception? To probe these questions, scientists combine the insights of geometry, physics, and observational cosmology, seeking to translate the abstract language of mathematics into tangible understanding of the cosmos. Observations of the cosmic microwave background radiation, the faint afterglow of the Big Bang, provide a crucial window into this topology. By analyzing this relic radiation for subtle patterns, astronomers hope to detect signs of the universe's shape. Large-scale structures, the immense filaments and voids formed by galaxies, further contribute clues. Imagine for a moment if the universe were shaped like a giant donut. Astronomers might detect repeating arrangements of galaxies appearing in different directions, a cosmic echo of the universe's underlying form. Such discoveries could fundamentally reshape our perception of space, suggesting that while our day-to-day experience feels flat and unbounded, the universe at its grandest scale could be far more intricate, curved in higher dimensions, or wrapped in ways that seem almost paradoxical. Understanding cosmic topology carries implications far beyond geometry. It could illuminate the very origin and eventual fate of the universe, potentially resolving long-standing cosmological puzzles and deepening our grasp of space and time themselves. The shape of the universe, its geometry, determines the limits of what lies beyond the observable cosmos, if such limits exist at all. Cosmologists have proposed several possibilities: a flat universe, a closed universe, or an open universe, each with profound consequences. In a flat universe, the most widely supported scenario according to current observations, space extends endlessly in all directions. Infinity is not just a mathematical abstraction here, it is a physical reality. In such a universe, there is no outside to speak of, only a continuation of galaxies, clusters, and cosmic structures stretching beyond the reach of our instruments. A closed universe, by contrast, is finite yet unbounded, much like the surface of a sphere. Travel far enough in one direction, and you could theoretically return to your starting point. In this topology, the notion of beyond becomes more complex as the universe loops back on itself. An open universe, with a hyperbolic or saddle-shaped geometry, would expand forever at an accelerating rate. In this scenario, vast regions of space could recede faster than light, forever inaccessible and perpetually beyond observation, a truly infinite frontier. The geometry of the universe and cosmic topology are intertwined in subtle and profound ways. Space-time curvature, as described by Einstein's general relativity, governs how massive objects bend the fabric of space and time, shaping the movement of matter and light, and giving rise to the phenomenon we call gravity. Cosmic topology, on the other hand, addresses the global structure of the universe, the overall connectivity and shape on the largest imaginable scales. Curvature plays a central role here. A universe with positive curvature might form a closed spherical cosmos, while negative curvature could give rise to an infinitely expanding hyperbolic universe. A universe with zero curvature, the scenario most supported by current measurements, appears flat on the largest scales, though even a flat universe could conceal intricate folds or connections, invisible from our limited vantage point. Our knowledge of cosmic topology comes from meticulous observation and sophisticated theoretical modeling. The cosmic microwave background radiation offers a critical clue. Scientists have mapped it with extraordinary precision, searching for subtle patterns that might reveal a finite or curved universe. These studies increasingly point to a universe that is remarkably flat, potentially infinite in extent. Complementing this, the large-scale distribution of galaxies provides another line of evidence. If the universe had a compact or looping topology, repeating arrangements of galaxy clusters might emerge, a cosmic fingerprint of the universe's hidden shape. Together, these observations continue to refine our understanding, bringing us ever closer to comprehending the grand architecture of the cosmos, a pursuit that challenges the imagination and stretches the limits of human knowledge. However, when astronomers turn their gaze to the cosmos, the vast expanse of stars and galaxies stretching across the night sky, they find no conclusive evidence of repeating patterns that might suggest a universe with obvious boundaries or a mirrored, infinite structure. Surveys of the heavens, conducted through powerful telescopes and meticulous sky mapping projects, have yet to reveal large-scale arrangements that would confirm the notion of a universe stretching without limit in any particular direction. Instead, the cosmos presents a more subtle, nuanced tapestry, one that requires careful interpretation through indirect clues rather than immediate observation. One of the most revealing tools for understanding the universe's shape is gravitational lensing. This phenomenon occurs when light from distant galaxies bends as it passes around massive objects, such as clusters of galaxies, warping the images we see from Earth. By analyzing how these distant celestial bodies are distorted, scientists can construct maps of space-time's curvature on cosmic scales. The results of these observations consistently point toward a universe that is remarkably flat, at least across the portions we can observe. However, flatness does not preclude minor deviations on scales beyond our reach, leaving room for slight curvatures that current instruments are unable to detect. Yet, the very notion of what lies beyond our reach introduces an essential limitation: the observable universe. This term refers to the portion of the cosmos from which light has traveled far enough to reach us, since the universe's inception, in the Big Bang. Anything outside this sphere remains hidden, cloaked in mystery, and impervious to direct measurement. Consequently, while we can infer the universe's properties within this observable region, the true global topology, the overall shape and extent of the cosmos, remains uncertain. This uncertainty brings us to two competing visions: the finite but unbounded universe and the infinite universe. In a finite yet unbounded universe, the idea of beyond becomes paradoxical. Consider the surface of the Earth, a sphere without edges. You can travel in any direction indefinitely and never encounter a boundary, yet the surface area is undeniably finite. Applying this analogy to the cosmos, a finite but unbounded universe would have no edge, no outside, making the concept of limitless exploration fundamentally different from our usual understanding. By contrast, an infinite universe continues endlessly in all directions, always containing more galaxies, more space, and more matter, with no ultimate horizon. In this scenario, the notion of beyond is simply a matter of continuing outward indefinitely, without encountering any closure. The implications of these models extend far beyond academic curiosity. A finite but unbounded universe suggests a possibility that traveling in a perfectly straight line over vast cosmic distances could eventually return one to the starting point, much like circumnavigating the globe. This challenges our intuitive understanding of space, making the cosmos feel simultaneously boundless and limited. An infinite universe, in contrast, aligns with the everyday perception of space as endlessly extending, reinforcing the idea that no matter how far one travels, there is always more beyond. These competing visions shape our understanding of cosmic evolution, the distribution of matter, and even the ultimate fate of the universe itself. Observations to date of galaxy clustering, cosmic microwave background radiation, and large-scale structure tend to support the notion of an extremely large, possibly infinite universe. Yet, the true extent remains tantalizingly out of reach. Within this context, the notion of a wraparound universe becomes especially compelling. Imagine a cosmic landscape where movement in a single direction eventually brings one back to the original location, as if the universe itself is looped. Here, the universe is finite in volume but unbounded in experience. Light and matter could theoretically traverse the entire cosmos and return to their point of origin, provided sufficient time. This idea fundamentally reshapes the concept of beyond, suggesting that space is a continuous self-contained system rather than an infinite stretch extending forever. If the universe is indeed wrapped in such a manner, it implies that space-time is curved on an immense scale, potentially forming shapes that defy everyday comprehension, multi-dimensional tori, or even more exotic geometries. While such curvature is imperceptible in local environments, it manifests when considering the universe in its entirety, offering a profound challenge to our intuitions about infinity, space, and the very meaning of boundaries. Closely tied to these topological considerations is the concept of the multiverse. Cosmic topology, concerned with the shape and connectivity of space, poses questions about whether our universe is flat, curved, or linked in unusual ways across vast distances. The multiverse hypothesis extends this inquiry further, proposing the existence of multiple universes beyond our own, each potentially governed by distinct physical laws, dimensions, or initial conditions. Certain models of cosmic inflation, which suggest a rapid expansion of space in the universe's earliest moments, predict the formation of bubble universes, each with its own geometric and topological characteristics. Quantum mechanics and string theory offer additional pathways to envision parallel realities or higher dimensional realms. Through this lens, our observable universe might be just one bubble among countless others, a single narrative in an infinite cosmic anthology. A related, deeply philosophical question emerges when considering the apparent fine-tuning of universal constants. Gravity, the speed of light, the strengths of fundamental forces, all seem calibrated to allow the formation of complex structures like stars, planets, and life itself. Even minor deviations could render a universe sterile, incapable of supporting any familiar form of matter. The anthropic principle offers one framework for interpreting this fine-tuning. Its weak form simply observes that we find ourselves in a universe compatible with life because we could not exist in an inhospitable one. The strong version suggests that the universe must possess properties that inevitably permit the emergence of life at some stage. Critics argue that these statements skirt explanatory depth, but supporters see them as valuable tools to contextualize our existence against the vast cosmic canvas. One possible resolution to fine-tuning lies within the multiverse concept. If countless universes exist, each with slightly different physical constants, then it is statistically inevitable that some will support life. Our universe, in this view, is not uniquely designed, but simply one among many capable of fostering consciousness. Another hypothesis imagines cyclical universes, with each cycle of expansion and contraction introducing subtle variations, eventually producing conditions suitable for complexity and life. Both approaches stretch our imagination, compelling us to envision a cosmos far beyond the limits of direct observation. These profound considerations, the shape of space, the possibility of wraparound geometries, the multiverse, and the fine-tuning of constants, collectively illuminate the extraordinary complexity and mystery of the cosmos. They challenge our intuitions, push the boundaries of scientific inquiry, and frame humanity's quest to understand not just what is observable, but the very nature of what might lie beyond. In confronting these ideas, we are reminded that our universe is simultaneously familiar and astonishingly strange, a cosmic arena where the edge of knowledge perpetually recedes, inviting curiosity, speculation, and awe. However, the anthropic principle remains a subject of intense debate and diverse interpretation among scientists, philosophers, and cosmologists. While some view it as a profound insight into the conditions necessary for life, others see it as nothing more than an observational artifact, a natural consequence of the fact that we can only exist in a universe capable of supporting observers. In this view, we are inevitably observing a universe compatible with our existence, simply because if it were otherwise, we would not be here to make any observations at all. This line of reasoning dovetails with the concept of a multiverse, a vast ensemble of universes, each governed by its own distinct set of physical laws and constants. Within such a framework, our universe may be just one bubble in an immense cosmic sea, a rare but not inexplicable exception where the conditions happen to allow the emergence of conscious life. This perspective transforms the anthropic principle from a seemingly mystical statement about cosmic design into a subtle reminder of the limits of human observation and understanding. It underscores that the remarkable conditions enabling life are real and awe-inspiring, yet they do not necessarily imply a deliberate creator. Instead, they invite deeper contemplation about the very structure of reality, the scope of our scientific reach, and the delicate balance that permits our existence. In the ongoing pursuit of knowledge, the anthropic principle occupies a unique intersection between physics, cosmology, and philosophy, a conceptual lens through which we examine the universe and our place within it. The principle manifests in two main formulations, each with its own implications and controversies: the weak anthropic principle and the strong anthropic principle. The weak version is, in essence, a simple observational statement. The properties of the universe we can observe must be compatible with the existence of conscious beings, such as ourselves. It reminds us that we should not be surprised by this compatibility because our very presence as observers presupposes it. This version is broadly accepted within the scientific community as it aligns closely with known physical laws and makes minimal speculative assumptions beyond what can be inferred from observation. The strong anthropic principle, in contrast, takes a bolder stance. It asserts that the universe must possess properties that allow life to emerge at some point in its history, suggesting that the constants and laws of physics are in some sense constrained or fine-tuned to permit the development of conscious observers. Some interpretations go further, proposing that the universe may be purposefully arranged to generate life, hinting at a cosmological intentionality. While the weak principle is largely treated as a logical observation, the strong principle provokes deeper philosophical and scientific debate, raising questions about the fundamental nature of reality, the potential existence of multiple universes, and the interplay between consciousness and the cosmos. Testing the anthropic principle presents a formidable challenge because it is not a conventional scientific hypothesis in the sense of being easily falsifiable. Nevertheless, researchers have outlined several avenues for investigation. One approach involves the study of fundamental constants of nature. Discovering or detecting other universes with different physical parameters could provide evidence that challenges the strong anthropic principle. Cutting-edge particle accelerators, deep astronomical observations, or even indirect cosmological evidence might one day reveal such alternate realities. Another line of inquiry examines the boundaries of life itself, discovering extremophiles, organisms thriving in seemingly inhospitable conditions, or creating artificial life forms adapted to unusual physical circumstances could expand our conception of the range of life-supporting universes, thereby diminishing the notion that our universe is uniquely hospitable. Computer simulations offer yet another tool, allowing scientists to model universe formation under diverse sets of conditions. If such simulations consistently produce complex, life-capable universes under a wide range of parameters, this might suggest that our universe's fine-tuning is less exceptional than the anthropic principle implies. Conversely, if simulations reveal that life-supporting universes are exceedingly rare, this would bolster arguments for a finely tuned cosmos. The anthropic principle also challenges our understanding of cosmic uniqueness. If our universe is one among countless others, as the multiverse hypothesis suggests, then its life-supporting conditions are neither miraculous nor unique. They are simply the circumstances that permit our observation. Yet, even in this scenario, the precise alignment of physical constants necessary for life highlights an extraordinary delicate balance, underscoring how finely structured our universe must be to allow the emergence of stars, planets, and conscious observers. Intertwined with the anthropic principle is the notion of observer-created reality, drawn from quantum mechanics. Experiments reveal that at the quantum level, particles can exist in multiple potential states simultaneously until observed, at which point they collapse into a specific outcome. This phenomenon suggests a subtle feedback loop between observation and reality. Combining this with the anthropic principle yields a provocative idea. If the universe must permit observers and observations can influence outcomes at a fundamental level, then consciousness itself may play a more integral role in shaping the universe than traditionally imagined. This blurs the boundary between objective reality and subjective experience, challenging the classical notion of cause and effect in the cosmos. Time, another fundamental dimension of our universe, becomes equally enigmatic when considered in the context of multiple universes or realms beyond our observational horizon. Within our universe, time is interwoven with space into the fabric of space-time, a continuum that governs the progression of events and the dynamics of matter and energy. Beyond our universe, however, alternative realms might obey entirely different physical laws, rendering our familiar notions of past, present, and future meaningless. Some theorists even posit higher dimensional structures where time as we perceive it is merely one of many temporal axes, or that time emerges as a derivative property of deeper, underlying phenomena. In such contexts, our current instruments and methods provide little guidance, leaving the true nature of time beyond our cosmos an enduring mystery. One compelling theoretical framework addressing these questions is eternal inflation, a cosmological model proposing that our universe is but one bubble within a perpetually expanding multiverse. According to this model, inflation, the rapid expansion of space, never completely ceases, instead continuing indefinitely in some regions while halting locally to form discrete universes like our own. These eternally inflating regions may experience time and causality in ways fundamentally different from our familiar experience, where rapid expansion can stretch space-time to extremes and conventional physical intuition breaks down. Within this framework, our universe is both ordinary and extraordinary, a single instance in a potentially infinite ensemble of universes, yet one where conditions happen to align precisely to permit the complex tapestry of life and consciousness that we observe today. In the end, the anthropic principle serves as both a lens and a question mark. It compels us to reflect on why the universe appears as it does, how deeply intertwined life and observation may be with the fabric of reality, and whether our existence is a fortunate happenstance or evidence of deeper cosmological design. Whether approached through the lens of physics, philosophy, or speculative cosmology, the principle challenges us to expand our thinking, probe the boundaries of what we know, and confront the profound mystery of why there is a universe capable of supporting conscious beings at all. Furthermore, the theory of eternal inflation offers a glimpse into a reality far grander and more intricate than our everyday experience of the cosmos. According to this framework, the universe we inhabit may be just one bubble in an endless cosmic foam, surrounded by countless other universes, each with its own timeline and physical laws. This raises staggering questions about the very nature of time itself. If multiple universes exist simultaneously, each with its own unique temporal rhythm, how can we even begin to reconcile these divergent flows? What we perceive as time, an inexorable march from past to future, may be a local phenomenon confined to our own cosmic bubble, while other realms could unfold according to entirely different temporal logics. In the context of eternal inflation, time may not have a definitive beginning at all. The universe's creation could be part of an unending cycle, a cosmic process that has been occurring forever and will continue indefinitely. There would be no singular starting point, no primordial tick that set the cosmos in motion. Instead, existence itself could be cyclical, an eternal unfolding of countless universes emerging, evolving, and perhaps vanishing. In such a framework, the familiar progression of seconds, minutes, and millennia is merely a localized pattern, one thread in a vast tapestry of temporal possibilities. Beyond our universe, time might behave in ways that defy our imagination. Some theoretical models suggest that time could flow backward or even sideways, challenging our notions of causality and consequence. Picture a universe where the future can influence the past, creating loops of events that intertwine in ways we cannot untangle. In other realms, time might not exist as a dimension at all. All events could occur simultaneously, with no discernible sequence or progression. Such ideas force us to rethink the very foundations of existence and consciousness. Some physicists even speculate that certain universes may have multiple time dimensions. In these exotic realities, beings might experience several timelines at once, navigating a complex web of temporal pathways. The implications are mind-bending. Inhabitants of such realms could move freely between moments, much as we move through space, witnessing events unfold in countless orders simultaneously. Other universes may experience time at radically different rates. A single second in one universe might stretch to millennia in another, or conversely, millennia might pass in a heartbeat. This variance would profoundly shape the development of life, the evolution of stars and galaxies, and the ultimate destinies of these cosmic neighborhoods. One theoretical lens through which scientists explore these ideas is the block universe concept. According to this view, Reality exists as a four-dimensional structure, with time as the fourth dimension alongside the three spatial dimensions we experience. Past, present, and future coexist simultaneously, much like different locations coexist in space. The flow of time, then, is an illusion, a product of our limited perception. This framework radically reframes our understanding of reality, suggesting that what we perceive as free will and change might be predetermined elements of an immutable cosmic tapestry. It also invites speculation about realms beyond our four-dimensional universe, other block universes governed by entirely different physical laws and dimensions, potentially infinite in variety and scope. Time's arrow, the relentless progression from past to future, is another key element shaping our understanding of reality. Yet, when we expand our gaze beyond our observable universe, even this seemingly fundamental principle comes into question. Regions beyond our cosmic horizon may experience time differently, with arrows pointing in opposite directions or flowing at disparate rates. The multiverse, with its multitude of universes, challenges the notion of a universal temporality. In some of these hypothetical realms, time could even reverse or cease to exist altogether. While in our universe, the arrow of time is closely tied to the increase of entropy, other universes might operate under alternative thermodynamic rules, allowing for phenomena unimaginable to us. Beyond even these scenarios lies the concept of timelessness, a state in which time as we know it simply does not exist. Without before or after, without cause or effect, all events would exist simultaneously. For minds accustomed to linear progression, this is almost impossible to grasp, yet it opens profound philosophical and scientific questions about the nature of reality. If time itself emerged with the Big Bang, then regions beyond our universe may exist free from temporal constraints, governed by mechanisms entirely alien to our experience. In such a timeless state, questions of beginnings and endings lose meaning. Aging, decay, and transformation might vanish, leaving a radically different conception of existence. Quantum theories further complicate the picture. They suggest that time might arise from deeper, more fundamental processes, implying that beyond our universe, entirely different mechanisms dictate the sequencing of events. This could give rise to realities where cause and effect operate in ways that seem impossible, where particles influence one another instantaneously across vast distances, or where universes unfold according to rules incomprehensible to human perception. Ultimately, contemplating realms beyond our universe forces us to confront the limits of our understanding. While direct observation remains impossible with current technology, theoretical physics allows us to imagine realities where the very fabric of existence is malleable, temporal structures differ wildly, and our most cherished intuitions about time, causality, and free will are challenged. These ideas, while speculative, push the boundaries of human thought, encouraging us to envision a cosmos far stranger, vaster, and more complex than our day-to-day experience suggests, reminding us that the universe we know may be but a single fleeting chapter in an eternal and infinitely varied cosmic story.